there are few slides are not very important. Thank you all for being here. I'm very happy to open the session and the workshop on advanced solution for the 6G satellite system. And let me go through. This is a very short introduction, and I'm very happy to see so many people here. The purpose of this workshop is to discuss, to have an opportunity for people to discuss and to progress in the research on satellite 6G, considering there is interest to progress in this direction after the 5G wireless communication progressing and spreading everywhere in the world. The workshop addresses as the purpose of the workshop is to address many issues starting from the role of satellite aspect concerning future application. The purpose is to have something supporting the bridging the coverage in areas that are unconnected. The purpose is so we will address architecture, network management, security, quality of service, and in focusing on the expected evolution of the standardization on non-terrestrial networks. This workshop, I have to thank a lot IEEE Future Network Initiative for giving us the opportunity to host this event. Every day we'll have so just a few logistic detail. Every day we have a keynote speaker. The second and third days, the keynote presentation will be not at the beginning, will be in the middle of the event of the day. We will have a Q&A at the end of every presentation, and a round table involving all the speakers at the end of each session that is coordinated by the session chair. We have collected the PDF version of your presentation. We are recording the videos. Thank you a lot for your participation. I take this opportunity to thank you very much IEEE and Matthew and Brad for their incredible support and strong commitment to help us to organize this event. I would like to thank also the track chair, keynote speakers, and all the presenters for their contribution. You see here the event. We try to organize to keep the different time zone into account. Today we start this time. The next 2 days we will start earlier to help people from Eastern region to join. So be careful, we are not taking the same schedule every day. Before I stop my introduction, I would like to show you a few related events. One is the Young Scholar Competition. You will find more detail, and you will have a better presentation later from the organizer and colleagues. Remember that here there are the possibility to submit paper and to contribute and to be selected for the award, to also to participate in this conference in November. And other related event is the Satellite Summer School, organized by StarTrack 5 project, and the related conference that is MS 2022, that is a very historical and very prestigious event that is organized typically in Europe every 2 years, where the satellite community is contributing. So I think that's all on my side. Again, thank you, Matthew, Brad, and I'm happy now to give the floor to Professor Ashutosh Dutta from US, introducing Future Network Initiative, that is the framework that is hosting our work. So, Professor Ashutosh, I'm very happy you to speak about the Future Network Initiative. Then we will have a welcome message from Dr. Sastrikota, and we'll have after the keynote from.
Thank you. Thank you, Giovanni. Appreciate the effort and you and your team has put it to get this to this stage. So let me see. Can you see my slide?
Yes, yes, I see.
Okay, let me just make it.
I will mute myself.
Okay, so you can see my slide. You can hear also. So Giovanni, thank you for the introduction. So I'd like to acknowledge a few folks, obviously Satellite Working Group and leadership team, Giovanni and Sastry have done a great job in nurturing this working group. I am one of the co-chairs, work for Johns Hopkins University Applied Physics Lab. Tim Lee is my colleague, IEEE colleague, and another co-chair. Like to acknowledge Narendra Mangra, one of the INGR co-chair, Brad Kloja, program director, and Matt Post, who is on the call today, who have been helping us nurturing this future network initiative for the last 6 years. So my plan is to give a little bit of overview of future networks and the INGR, the roadmap that we are developing, and satellite working group is one of them. So we started this working group about close to 6 years back and started like IEEE 5G initiative. And at that point, we decided to move it to future networks because we are not only looking into 5G, 6G, 7G, so 3 or 5 year, 10 year, 20 year from now, how things are going to look like. And I'm going to talk a little bit about how you can benefit from this initiative, how you can contribute to the next generation evolution of networks. And obviously, satellite working group is one of the part and parcel of this initiative. So, being within IEEE, this is incubated, which in Future Direction Committee, which is responsible for defining the emerging technologies. Out of 46 or so societies, there are more than 22 societies who have been involved in many ways, right? Because if you look at future networks, it spans across all aspects, from physical layer all the way to the application layer, and including the systems and end-to-end. So there is a room for everybody who has been working in communication technology to contribute to this effort. There are many aspects of this future network initiative. It's almost acts like a mini society. These are different pillars. We collaborate with multiple societies within IEEE. There are content part. We have technical newsletter, podcasts, videos, articles. There is publication standards. I will go over that very soon. There are conferences, workshops like this. Some of the flagship conference like Future Networks World Forum, it used to be 5G World Forum, it's been going on for the last 5 years. IEEE Connecting the Unconnected Summit, this is the second year coming. And there are other relevant workshops like Fast Responder Tactical Networks, Next G Summit, etc. And last but not the least, we also have this roadmap which defines what's going to happen 3 year, 5 year, or 10 year, 15 year from now. We also collaborate with IEEE Standards Association and other OUs outside IEEE so we can collaborate together. There are multiple webinars every month, tutorials, white papers, e-learning. So every aspect of education standards, publication, conference, industry engagement, we do look into that. So this is how the organization is structured, just to give you an idea. Brad Kloja, we couldn't join today because of other commitment, but we have education publication, roadmap, conference events, standards, test bed, industry engagement, and I'll focus a little bit on the roadmap side. Just to give it a highlight, Satellite Working Group is one of those 15 working groups, and there are more than 100 plus volunteers who have been working towards it. So that if you want to contribute to it, you can contribute in any of these working groups. There is a web portal, futurenetworks.IEEE.org. If you go there, there are lots of resources. I'd like to thank Matt and his team making this really enriched resource for folks to look at. So please go and visit futurenetworks.IEEE.org. In terms of conference and events, this Future Networks World Forum is coming up in Montreal. The call for papers is still open, July 31st. There are many ways you can contribute to that. We have this Fast Responder Tactical Networks. So we have been doing that at Johns Hopkins for the last 4 years. It's going to continue at PIP here as well. We have collaboration with Department of Homeland Security, DOD, etc. Connecting the Unconnected. This is a new one. We wanted to see how we can contribute to reduce the digital divide or take care of it in a way. So this was partly sponsored by New Initiative Committee. This is happening again in 2022, first week of November. So the deadline to submit 500-word abstract for competition is tomorrow, which is July 20th. So if you haven't done it, if you have some interesting idea, please do submit there. Just like this workshop, the satellite workshop, we have done 6 or 7 of those in the past. And so we continue to focus on the workshop based on the roadmap technology work group, so that people who are interested, they can join, they can learn, they can contribute. There's a publication working group, Tech Focus. We give a chance to folks around the world in an open, neutral way, work in progress. You also have a chance to submit to any specific journal, magazine articles. So please let us know how you can get involved here. As I said, there is a standardization building block group. So some of the potential work items from the working groups can make its way to IEEE standards. So we have a standardization building block group that work with the working groups and pick those standards. So some of the recent things that have happened that came out of Future Network Initiative, I have listed here: transdisciplinary framework, telehealth. Very recently, we started this Open RAN initiative. I'm actually one of the co-chairs there. Narendra is the co-chairs for others. And there are rapid reactive standards activities where we look at potential topics that can be standardized. And Mehmet and Alex, and they take it to Standards Association on ComShock. So it kind of acts like incubation for potential new standards. So for example, satellite, there may be some new standards that can be used and potentially discussed within the satellite working group, and the standards group can take it to the next step. So, and you know, this is a good way to get some visibility, and some of the things which are lacking or the gap can be done. This is the most recent one. IEEE board just approved last November. So traditionally, IEEE has been mostly on paper journals, things like that. And this is a unique initiative, again, led by Nick, New Initiative Committee, where we are building a virtual testbed and making it open for the operators, vendors, and applications service providers, startups to come and try to develop some use case end-to-end. So Anwar Aldwani, Brad, myself, Josh, a few of us are spearheading this effort. That is if you're interested to learn more about it, please get back to us. We already have operators, vendors, they are lined up as the founding members. We are in the process of getting this lab set up. And this also has potential contribution from the educational institution like university. They can also take advantage of this. So please take a look at that. Now getting into the roadmap, I'll be quickly going through it. So as I said, roadmap, main intention is to develop the technology or forecast the technology in terms of its KPIs, etc., how it's going to look like, because that's how we define the next steps, right? It's could be 60 or 70, whatever. So I'd like to thank the working group co-chairs, Narendra Chiming and Rose Zhu. And primarily, we have categorized in the access, network components, performance, system standards. And if you see, the satellites is one of the primary access category. Satellites deployment, connecting the unconnected, edge automation, massive MIMO, systems optimization, optics. Then on the systems and standard side, we have energy efficiency. So if you, and finally, the service enablers, security, application services, and AI ML. So these are like 14 different working groups. And they meet twice a month, discuss various things, how to contribute to the roadmap. We also invite speakers, talk about new technology that's coming up, collaborate with ITU, 3GPP, and others as well, right? So this is the scope. As I said in the beginning, we recently published 2022 editions. And with the help of the volunteers working group from these 14 working groups, which I mentioned, and it is already available. You can take a look at it. I will briefly go over that. Now we are already started working on 2023 edition. So if you're interested, please reach out to us. So these are the working groups. If you go to the Future Networks IEEE.org roadmap, you can see application services, AI, ML, CTU, deployment, edge automation, energy efficiency, massive MIMO, millimeter wave, optics, satellite, security, privacy, standardization, building block systems, optimization, test bed. So as I was telling, we have been doing this workshop for each of these roadmap working group. So this being the satellites, this is probably the 7th or 8th workshop. Some of the previous workshops have been recorded. You can take advantage of that, go to the website and get access to those. And they'll also be available in IEEE TV at some point. I'll just briefly browse through it. I don't have time to go over each of these. There's a CTU working group what is the focus there? Connecting the unconnected digital divide. Satellite working group, Giovanni and Sathri, obviously they are leading this. It's been a very, very comprehensive report. If you haven't read it, please do that. Otherwise, you're going to miss a lot of things. Very technically rich document. Working, and they're looking into some of the deployment issues, environmental issues. There have been podcasts around it. So different public sector, municipality, and so that's another interesting working group. Massive MIMO working group. They have been doing a lot of fundamental research, how to extend the existing massive MIMO technology to the next steps. And there have been potential standards contribution as well from massive MIMO. INGR optics working group, recently, a little bit relatively recent working group. There have been a lot of improvement there in terms of how to have the converged networks, right? So you can take a look and figure out if that is your interest. You can learn, you can contribute there. Millimeter wave signal processing led by Team Lee. There are things like what is the next spectrum, terahertz, gigahertz, terahertz, etc. Those are the things you can look at there. Edge services automation to support ultra low latency type applications. Prakash, Sujata, they are leading that. As you can see here, some of the things as an example of the metrics, the KPIs, how things are going to look like in terms of throughput, latency, jitter, reliability, etc. Right? So these are the things you're looking into. Systems optimization helps to provide algorithms, techniques to optimize the systems end to end. Energy efficiency working group looking into some of the reduction of energy associated carbon footprint to make the global communication more optimized. Testbed working group led by Yvonne and Mohammad Patwari. They are looking into how some of these use cases can be used to, we can take advantage of some of the use cases to develop proof of concept. So I talked about the virtual testbed, but we also have access to testbed like Rutgers WinLab. And we are developing a best current practice, how to use the testbed, set up testbed out there in the world that you can get access if you want to do any specific proof of concept. Standardization building block, I already talked about it. Reinhard, Alex and Mehmet, they have been leading this. Then application services working is very, very important because all driven by that. Narendra Bhangra is one of the co-chairs. You have lots of different vertical use cases, agriculture, e-health, entertainment, so on and so forth, right? The past responder, you can actually take a look there. And in fact, the public safety initiative initially was incubated here. Now it is a completely new initiative that came out of this application working group. AI/ML is the most recent addition, is another enabler. I and Deepak Kapadia is one of the co-chairs. Security working group, I personally am involved along with Iman. This cuts across all the working groups. So you got a preview of the 14 working groups and what they are doing. You can get access to those by using this link. This is completely free for IEEE Society members with a nominal price. You can join, become FNI member, and get access to this rich content and be able to contribute. I mean, you can contribute anyway, but if you really want to get access, you can follow this process. Last slide. The contact information, what I have provided here, the co-chairs, and how do you list out? I mean, reach out to these co-chairs. They're all listed here, different working group, co-chair, working groups and the co-chairs, and the email list that you can send. So this goes to the co-chairs and then you'll be added, then you can attend. Some of the contact points on the left-hand side are listed here. The FNI co-chairs, INGR co-chairs, Matt and Brad, IEEE staff. So with that, I'll hand it back to you, Giovanni. Thank you for giving an opportunity to introduce FNI and talk about INGR. And I wish all the best for a very nicely organized satellite workshop, all the attendees and distinguished speakers.
Thank you, Professor Ashutosh, for giving this very nice overview of the Future Network Initiative. That's the framework where we are contributing. I think the work you presented is impressive. So thanks a lot for this nice talk. So now, thank you. Now I would be happy to introduce Dr. Sastry Kota, Sohum consultant. He is the co-chair and the leader of this satellite community. And I will be happy to give the floor to him, giving a welcome introduction to this workshop. I'm sharing the slides, just a second. And presenting, I need just a second. Hi, Sastry, can you see the slides? Hi. Okay, hi, Sastry, do you see the slides? I think I've shared it on.
Yes, yeah. I do. Thank you.
Great.
Okay, should I start?
Yeah, yes.
Good morning and good afternoon and good evening, depending on where you are. I'm Sastry Kota, as mentioned, and I'm the co-chair of this International Next Generation Roadmap. Okay, next one, please. Next chart. Next chart, yeah. It gives me a great pleasure to welcome you all to this workshop that is Advanced Solutions for 6G Satellite Systems. It gives me immensely happy to welcome the keynote speakers, the track chairs, the presenters, and all the attendees. I especially appreciate the planning and organizing an outstanding satellite workshop, especially Giovanni, Brad, Ashutosh, and Matthew have done an incredible job to get this workshop going. So we'll see more about it. Thank you. Next one, please. Next, yeah. The satellite systems play a significant role as a complementary solution for this ubiquitous 6G coverage and to meet the emerging applications and services. The purpose of this workshop is to address various key solutions for 6G realization. As you see, already we have 5G implemented many a time, but most of the vendors. And 6G is going to happen very soon. But then the system architecture, network management, security, and KPIs, QoS, QoE, etc. We need to address those, and we have to find the solutions. There are 3 keynotes today. One is each day we have one. The first one today is going to be by Nelson Melgotti. He's from ITU Geneva, and he's going to talk about the vision and requirements for satellite radio interface, the IMT 2020. The next one is Professor Simon Schatzinotas. He's from University of Luxembourg. He's going to talk about 6G satellite communications. Is a hype or a reality? And then the third one is Prasad Bhatt. Dr. Prasad Bhatt is from Astrom Technologies, India, addressing the challenging landscape changing for the global connectivity. So those are the 3, and you'll have an excellent talk about it, especially today's. We have been working with Nelson for a long time at ITU, and it's going to be a wonderful talks for the next couple of days. This chart will try to give you some idea about the workshop, what we have. There are 4 tracks, and each day, I mean, there are the papers selected and accepted, and also some of the statistics. That is what we are going to talk about it, the next couple of charts. The first one is there are 4 tracks in this, and the track chairs John Bass, and then the Professor Zil Sun from University of Surrey, and Paresh Saxena from BITS Pilani, India, and Tasneem Darwish from Carleton University, Canada. So those are incredibly, they selected this, selected the papers, accepted the papers, went through, there is an excellent type of tracks which we are going to see. The first one today is physical layer for 6G non-terrestrial networks, NTN. And the second is QoS, QoE, performance evaluation, and KPIs for 6G networks, satellite networks, of course. There are 8 papers. And then the third one is edge computing and intelligence for satellite 6G by Paresh. And the future, the last one is the future satellite network management. And all of them have been the members of this workshop. And the last 2 years, they have been incredibly contributing to the working group. And it's going to be, I think you guys, who are attendees, they will be taking away with this workshop something very interesting. And at least it will help you to the research to solve some of the problems for the 6G network. I'm very happy to announce that we have about 16 countries participated, selected for the papers for this workshop. So the next chart, please. So as you see here in this table, which is represented in a different way in the previous chart, that is the same thing, that Saudi Arabia, China, Germany, Canada, United Kingdom, and India, Luxembourg, and Japan, Korea, Italy, USA, of course, and Sweden, Spain, Ireland, Finland, and Australia. So there are about 16 countries participated. I think that is a wonderful mix of all to address the 6G, which is going to serve the countries in various ways, just as anything else. Right now, the 4G, 5G, and so on. Just like that, we are going to have, and it is going to revolutionize completely the way the life, how the people are living, and how the action. We think that it's already changed the way the lifestyle is today, but it is going to be much more changing for the next 6G when it becomes realizable. But of course, we have to do a lot of work as engineers and and the scientists, we need to work on that. The next chart, please. I just want to give a historical note before we start this chart. Arthur Clarke's paper on extraterrestrial relays and predictions of communications by geosynchronous satellites in 1945 made it possible today, the satellite communications as of today. Later on, organizations such as Intelsat and Eutelsat are established. Most of the satellites were geostationary Earth orbit or geosynchronous satellites, both for military as well as these commercial applications. But in 1990s, if some of you remember, the Ka-band systems were developed, and Lockheed, for example, Lockheed Martin developed this Astrolink. Hughes, I think currently the Boeing, the Spaceway at the time, and TRW, which is of course now it's called the Northrop Grumman. It developed the Odyssey, and Europe has started the Euro Skyway. They developed all these, but most of them are geo satellite systems. There is only one at Ka-band that was only the LEO systems developed, is called the Teledesic, with 840 satellites, later on changed to 288, and eventually it was the Motorola changed from the LEO to MEO systems with the 32 satellites actually. But out of all these, at some point or other, either they changed the business plans or they completely off the development process. So why it happened? It's not because of the technology is problem, but it is because of the financial situations, as many of you remember, 2000, what happened at that time. So that is why, and also Iridium and Global Star, as the Nelson will be knowing very well about Dave Weinreich, who was coming from the Global Star. They both are the LEO systems and still, I think, operating. Of course, they had some issues in between, they had to change. But now, the last few years, they both of the changing about the satellite systems, which there are various, the data rates and the number of satellites. Out of all these, as you see, 5 of them, one of them is the MEO system, the rest are all the LEO systems. So out of the LEO systems, as you see, there are 44,000. They are applied, and then already FCC has approved to many of them. So you see much more on these as we go through the next chart, please. Next chart. As you see here, this 6G applications, mainly the healthcare and autonomous cars, manufacturing, the precision agriculture, the soil, the moisture, the measurements and the precision, the temperature and the trees, illness, etc. Those are all the precision agriculture, and the education. Those are all the various applications which are going to be solved by 6G application. At least the internet access is not around the world. There is only 2.9 billion people are still offline, as you see. And similarly, many of the passengers on the aircrafts and high-speed trains, highways, etc., they cannot get an access to this. So that is where the satellite will have much better application. The next chart, please. Next chart. Yeah, here you will see only the problem, as of course the data rate and the KPIs are given between 5G and 6G, you can compare. But the main thing is in the latency. This is 5G is 1 millisecond, whereas it is a few hundred microseconds as we talk about. This is one of the challenges for the architecture definitions and how you get it. And the jitter is not specified for 5G, whereas it is specified for the 6G, for the video applications. So the next chart, please. This provides the non-terrestrial networks, what we have at the observation, navigation, and communications purposes. There are geo satellites, LEO satellites, and also the high altitude platforms and the unmanned aerial vehicles. These are all the network for those. So, but there is a special, the terrestrial networks, which are for the mobile broadcasting or the broadband, etc. But basically, it is the combination of the architecture is with LEO and high altitude platforms and UAV, how to address both of these as an architecture. You will hear more about it from the topic presentations. Yes, next chart, please. This is another way of representation. The other way of representation of the space airborne network and terrestrial networks. So this is the altitudes and the number of satellites and etc. The next chart, please. Next one. This is the machine learning and AI applications for the position, application, security, resource management, physical layer, and network planning. Various applications which we can do, and then various addresses. We have to address the multiple access or the jamming, depending on the security issue or the position issues. The next one, please. Now the next, as Ashutosh already mentioned about it, but about the satellite working group, the next third year activity, we have focused on the 6G mainly, and also extend some of the work on the new system architectures, the focusing on the physical layer, network management and impact of the edge intelligence of the system, the security aspects, and the various industry and standardization is one of the important with between the ITU and 3GPP, interactions with other unconnected, connected, and also the security working groups. Yes, the next one, please. This is the last year's report, as Ashutosh already mentioned to you. If you need to get access to this, this is the website or the link, and also study to this report. It is an exhaustive, and its various aspects are published in this. And please go through this if you have some time and interest. Okay, the next one, please. Regarding the satellite working group, we have about 46 members from the 15 different countries. They're all involved, and we meet every 2 weeks, once every 2 weeks, and with WebEx. And these are all, if you are interested in participating and contributing to this and addressing some of the issues of the 6G, this is the links are given, and the send it an email to Matthew or Brad, then they can through this use these links, and then you can get an access to the system. Okay, the next one, please. I think we covered most of it, and I welcome you all again for this excellent workshop. And I'm pretty sure that you will take away with you some of the interesting ideas and the solutions. It will help you on your research. And let's begin, and we'll see what the next keynote is going to be. Nelson, it's good to see you. Good to hear from you. Thank you.
Thanks a lot, Sastry, for your interesting presentation. I think we can now hand over to the first keynote. I'm very happy to, just a second, that I have I'm very happy to introduce the first keynote. I will introduce very quickly. Is Nelson Malaguti from ITU. The title is Vision and Requirements for Satellite Radio Interfaces of IMT 2020. Nelson is Counselor of Radio Communication Bureau of the International Telecommunication Union. He is responsible since June 2006 of ITUR Group 4 on satellite services and coordinated. He was working on satellite since many years. He has received a master's degree in telecommunication from PUC Rio, Brazil. And he is working actively on work conferences and especially working on towards the next work to 2023 that will be next year. So Nelson, it's a great pleasure to have you here, and I give you the floor, and I will stop my introduction. Thank you so much.
Thank you very much, Giovanni, and thank you very much, Sastry. It's a pleasure to see you again, and it's a great pleasure to be here to participate in this event. Let me share my screen.
Yes, please. Thank you.
Yeah, okay. So again, good morning, good afternoon, and good evening. So as Giovanni mentioned, my name is Nelson Malaguti. I'm the counselor for the ITUR Study Group 4 dealing with the satellite services. So first of all, I really would like to thank very much the Satellite Working Group and the IEEE Future Networks Initiative for this kind invitation and opportunity to present the current work within the ITU radio communication sector on the vision and requirements for the satellite radio interfaces of IMT 2020. So IMT 2020, this is the naming of ITU, which corresponds to 5G. So I know the main topic of this event is 6G, but we are not really there. I mean, we have not yet started the standardization process of 6G, but we are trying to go very quickly and finalize this standardization of the satellite component of IMT 2020 or 5G. I have a couple of slides just to show more, show you about yes,
Nelson, sorry. We don't see your slides. Probably we have
sorry, let me.
You have to click on on the green bottom on the window.
Sorry, yeah. Now I think you are seeing it.
Great. Yes, thank you. Well,
let me just. Let me just. Okay. Yeah. Okay. So sorry, I forgot to share the screen. Sorry about that. So, but in any way, we are still in the first slide. So So as I was saying, we are trying to move quickly, to move fast in the standardization process of the satellite component of IMT 2020 and the 5G. So I was talking about what the ITUR Study Group 4 is doing. So is the ITUR Study Group responsible for satellite services, and we deal with the FSS, Fixed Satellite Service, BSS, Broadcasting Satellite Service, and MSS, Mobile Satellite Service, and also the RDSS, Radio Dissemination Satellite Services, which encompasses the RNSS, the Radio Navigation Satellite Service. So in this slide, I show you here what are the hot topics. I should say the hot topics currently being discussed in ITUR Study Group 4. So as you can see here, we have systems, air interfaces and performance in FSS, BSS, MSS, and RDSS. We have this efficiency of the spectrum utilization for FSS, BSS, MSS, and IDSS. And we have, you see in the fourth bullet, one of the hot topics is indeed the theme of this presentation, the vision and requirements for the satellite radio interfaces of IMT 2020. It's 5G. We have also early warning and relief operations and systems and networks in the RNSS. So we are conducting many studies and producing a lot of outputs, mainly recommendation and reports related to that. For instance, on this efficient opt-in spectrum utilization, as it was mentioned previously, we are now doing a heavy work related to the next World Radio Communication Conference, WC23. So in particular, one of the working parties of Study Group 4, which is Working Party 4A, is responsible for many agenda items for the next conference, dealing with many issues relating to geo and non-geostationary constellations and Earth stations in mobile platforms, or Earth stations in motion, as we call it. So there are many documents and recommendations and many reports being developed on that. We are developing now a report exactly on vision and requirements for the satellite radio interfaces of IMT 2020 or 5G, which is I'm going to show you in the next slides. We have also, relating to early warning and relief, we have also developed the many recommendations and reports on the use of the mobile satellite service and fixed satellite service systems for warning, response, and relief operations in the event of disasters. And finally, we also developed many recommendations and reports related to systems and networks in the radio, in the RNSS, the radio satellite systems. For instance, characteristics and protection criteria and terminal related to GPS, GLONASS, Galileo, Beidou systems. So we have a lot on that. Going to the next slide. Yeah, so it's just here you can see how the study group 4 is structured. So we have the 3 working parties, Working Party 4A, which is dealing with the efficient opt-in spectrum utilization for FSS and BSS, Working Party 4B, systems, area interfaces and performance and the ability objectives for the services, and in particular, Working Party 4B is the working party dealing with the developing now this report on the vision and requirements for satellite radio interfaces. But I mean, in addition, is the working party dealing with the all standardization process for the satellite component of IMT 2020. So after this report, we start the work of a recommendation with the detailed specifications of radio interfaces, and that work will also be conducted within Working Party 4B. And finally, we have Working Party 4C, which is dealing with efficient opt-in spectrum utilization for the mobile satellite service and the radio determination satellite service, which encompasses, as I said, the radio navigation satellite service. Now, so going to the topic. So, as I said, the ITUR is currently developing a new report on the vision and requirements for satellite radio interfaces of IMT 2020. The purpose of this report is to build a vision and the requirements for the satellite component of IMT 2020, including use cases, application scenarios, capability systems, radio interface, and the considered specific features, particularly with respect to service and technical requirements. And in addition, this report provides evaluation criteria and methodology for evaluation of the requirements in order to develop the recommendations for the detailed specifications of satellite radio interfaces of IMT 2020. The usage scenarios for, I would say, the terrestrial component of IMT20 and beyond are the what we call enhanced mobile broadband, EMBB, I would say, massive machine time communications, and ultra reliable and low latency communications. But what you can see in this slide is the use cases for the satellite component of IMT 2020. The satellite networks will provide, I would say, satellite versions of that, which we are calling now enhanced, as you can see in the slide, enhanced mobile broadband satellite and massive machine time communication satellite. And so this suffix S in the naming, the idea is to capture here the specificity in terms of the expected performance for the satellite. I should say that the satellite component of IMT 2020 will not address what we call for the terrestrial component, like ultra reliable, low latency communications, but we'll cover what we call satellite specific high reliability communications, as you can see here in this slide. And then for this specific use cases of EMBB and massive machine time, you can see here the specific use case, but I will cover that point, those points in later in this presentation. Going to the next slide. So the satellite component of IMT20 is expected to support many different applications and scenarios, which will include IoT, Internet of Things, and transportation. So the satellite component can be used, as you can see in this slide, to provide, for example, global connectivity to enhanced mobile broadband satellite and IoT or massive machine time communication and user devices. Also for network resilience through high availability combined with high reliability. Connectivity for transportation purpose, as was mentioned by Sastry, Dr. Cotter mentioned previously, and also content delivery in broadcast or multicast modes to mobile terminals or IoT devices. So, as I said previously, here you can see more specifically what we see like use cases for the enhanced mobile broadband satellite. So we believe that it will support high data rate applications over suburban, rural, and remote areas, as well as air and maritime environments. We also believe that the large, especially for the air environment, we believe that the large velocity of the terminal devices shall be supported to meet this transportation needs. So more specifically, we have this following use cases, as you can see here: coverage continuity for moving pedestrian and vehicular users so that they will be able to maintain access to a large range of communication services while moving. Of course, this is one of the main goals of the satellite. I mean, connecting populations in unserved or underserved areas. As already mentioned, connectivity to transport, mainly I would say buses, train, but mainly in vessels and airplanes, and also public safety. So to provide communication services like messaging, voice to emergency responders. Continuing on the two other general use cases. So the massive machine time communications provided through the satellite component of IMT 2020 will be able to address, we believe, will be able to address a large number of scattered connected fixed or mobile devices over wide areas. So such devices, we think, would be low cost and have a long battery life. And so several use cases typical of the massive machine time communications are identified here. As you can see, so we have automotive, so traffic. So this is mainly to include traffic flow optimization, automotive diagnostic, and safety status reporting. Utility, so this is mainly for surveillance of infrastructures like oil, gas, or energy, water infrastructures. And again, to transport. So this is mainly for fleet management, asset tracking, and remote roads alerts. And finally, the high reliability communication scenarios has also some specific requirements for availability and reliability. And so the typical use cases, as you can see here, for remote control of critical industrial applications, unmanned aerial vehicles, transportation safety, and humanitarian medical support. So now I have a couple of slides to show an example of the typical system scenarios, which one is based on transparent and another one on regenerative payloads. But before going into that detail, just like to mention that what we think is that the integration and or interworking, by the way, there's a good discussion within Working Party 4B now on the definition of integration and interworking. But in any way, we believe that the integration and or interworking between the satellite and the terrestrial components of IMT-20 is really relevant in order to effectively utilize the respective areas of strength of each of those components. So we believe that interworking systems will rely on the technologies to switch between the satellite and the terrestrial components of IMT to enable the user to receive the best connectivity available. And in addition, we believe that the terrestrial and satellite networks can complement one another to meet the requirements for additional capacity and coverage in any areas, including those areas underserved by the terrestrial IMT. So the figures, so I'm showing now the first one, will illustrate two typical system scenarios where the satellite implements respectively a transparent and the second one a regenerative payload. So as you can see in both cases, as you can see here in the first figure, the satellite radio interface is this red arrow here, implemented between the satellite and the user equipment. And we have the other links here, the feeder links. The next slide will show the inter-satellite links and also the satellite access nodes and the gateway, which are here for information. The idea is to show the overall operational context of the satellite radio interface. So in this first figure, so you have a transparent payload, and in this next figure, it's the scenario based on a regenerative payload. And so as you can see here on the second figure, you have like the first one, you have the service link with the satellite radio interface here, but you have the possibility to have an inter-satellite link. And because you have the regenerative payload, you have a kind of you have onboard process, which means that different from the first slide, where I'm showing again here, the satellite access node is here in the gateway. Here we have a split. We would have an on-ground unit of satellite access node and an onboard unit for the satellite satellite access node, which means that we can have some protocol-related base station functions that are also located, can be on ground and on board. And here we can have some onboard processing and mainly for routing and switching. So this will allow this. Yeah, for signal processing, routing and switching. Now, the next slide here, I wanted to show to you our current schedule for the development of the IMT 2020 satellite radio interface recommendation. This is the final goal. What we are developing now is a report on the vision and requirements, but of course the goal, the objective of the whole process is to define and to produce a recommendation on the detailed specifications of the radio or satellite radio interfaces of IMT 2020, like we did previously for what we call IMT Advanced, which will be corresponding to 4G. So here, what you can see, basically, this is the similar schedule as was done for the IMT, for the development of the IMT Advanced, but it's more, I would say, compressed in time. We are trying to do things faster now. We started a little bit late, but we are trying to recover time. So that's why we are compressing in time and trying to move really, really fast on that. So this figure, I will show you the next slide, which shows in detail what are these steps 1, 2, and 3, and what are these critical milestones. You can see here 0, 1, 2, 3, and 4. Let me show you the next slide. So here you can see what are the steps. So the first step is the issuance of this circular letter, which will invite the submission of candidate radio interface technology and set of radio interface technologies. So this will be the first critical milestone, which is the issue of this invitation letter, which, as you can see here, is expected to be in September this year. And the reason is that this report that I mentioned, hopefully, I mean, that's our objective. This will be finalized at the next block of meetings of Study Group 4, which will take place in September. And with the meeting of formal meeting of Study Group 4, which will hopefully approve this report on the vision and requirements. With the approval of this report, we can issue this circular letter with an invitation for candidate radio interface technologies. So the goal, as you can see here, is to receive this candidate radio interface technologies and go through all this process that is shown here with the evaluation and consensus building and the decision. And the final goal is to have developed this recommendation on the detailed specifications of the radio interface, of the satellite radio interface for IMT 2020. And then you can see here the expected deadlines. All this is our idea. All this, of course, will be confirmed at the next block meetings in September. So, next slide. So here, I would just like to provide you an idea of what are the typical terminals that we are considering in this report on the vision and requirements. So we have basically 3 types of terminals. We have a handheld terminal, we have a directional terminal, and we have a machine type the terminal, what we call a machine type device. So, of course, we think that the satellite component of IMT 2020 will provide differentiated services to end users according to the terminal types. So we have the handheld, which is a handheld or handset available to the general public. So this basically, it's the antenna type, it's an omnidirectional antenna. We have the directional terminal, which is basically a terminal mounted on a moving platform like aircraft and vessels. And this is the idea, is to provide connectivity to users on board these platforms. And this is basically, as I said, a directional terminal, a directional antenna. And finally, the machine type device, which is basically sensors which will provide transmissions of short packets and also having the ability to receive short packets. And this, again, the antenna type here will be basically a omnidirectional antenna. Regarding the handheld here, terminals, we believe that systems providing service to this handheld devices are of course expected to have a sufficient gain power and receiver sensitivity to establish communication with end user devices. So thanks to the recent developments on the satellite technology, for instance, large space station antennas, which can provide a high gain and also multiple reconfigurable spot beams. And these are some kinds of key attributes for the integrated systems. So this will really help the satellites integrated with the terrestrial in order to serve the mass markets terminals, which we believe will operate on both the terrestrial and the satellite components, so that the user equipment of an interworked or integrated system could have the ability to select the relevant component, either the satellite-based or the terrestrial-based component, to keep a given service quality over a wide and continuous service area. Finally, the last slide here. Yes, the technical requirements. We believe that due to the wide coverage, resilience, and multicast and broadcast capabilities, we believe that the satellite systems can provide a really efficient network solutions. We believe that the satellite IMT component will definitely expand the benefits of satellite IMT 2020 use cases and associated service requirements. And of course, we think that both geostationary and non-geostationary satellite systems, of course, have a role to play in this context. We have the technical requirements related to the technical performance for candidate satellite radio interfaces are described here. As we mentioned, the satellite component of IMT 2020 would be complementary to the terrestrial component in order to provide an ubiquitous and reinforced availability of the services. In particularly, the satellite component can effectively offer services in certain regions beyond the terrestrial coverage. We believe that regard, as I said, the main targets of the satellite component would be suburban, rural, maritime, and aeronautical environments, as I mentioned before. But what we think that the technical, because we would like to see the satellite component complementary and compatible with the terrestrial component, The idea is that the satellite component should adopt to the extent possible, of course, the same definition of the technical parameters, exactly to allow this compatibility and be complementary to the terrestrial component. So what you see here in this slide, this list of technical requirements are exactly the same as those for the terrestrial components. I'm talking about the definition, but of course the values and the performance targets would be defined for the satellite so that it will take the specificity of the satellite environment. But keeping the same definition would allow to be compatible and to compare with the minimum requirements of the satellite components. I didn't include specific values for each of those requirements exactly because we are, as I said, we are finalizing this report, and there's a lot of discussions on the values. Currently, we are going to finalize in September, and for each, of course, for each of these technical parameters, there's a value for each of the 3 types of terminals that I mentioned in the previous slides. So this is currently being discussed. So the values are changing, so they will be finalized in September. But that's why I didn't include here, because they are not finalized. But I will be certainly happy to include them in the next version of this presentation with the final values. Then I can, with the formal report, with the report being formally approved, I would be able to show what are the exact minimum requirements for the satellite component, its exact values expected for each of those technical requirements listed here. So with that, I would like to again thank you very much. Thank you very much for your time, and thanks very much for the organizers for giving me the opportunity to make this presentation. And again, as we finalize that in September, this report, I will certainly prepare an updated version of this presentation based on the formally approved report. And as I said, we hopefully approving this, we will issue this circular letter and with an invitation, as I said here, I'll just put again here, with an invitation for candidate radio interface technologies. So this is very welcome, and I should say that this includes even non-members of ITU that could make proposals. So we have an ITUR resolution allowing for that, the participation of non-members of ITU, and even for the evaluation, it can even we can have even independent groups of evaluation, which can also encompass non-members of ITU. Of course, the idea is to help to achieve a consensus on the proposals that we hopefully will receive after following the issuance of this circular letter. So again, I would like to thank you very much. Many thanks.
Thanks a lot, Nelson, for your nice talk. I think we have many questions. So I don't know if there is a question from the panelists. Otherwise, I will. So in any case, panelists can pose a question anytime. I think we can start to go through the question they are provided. So there are many. So one is discussing about the satellite component of IMT that is discussed during the working package 4, but it says that the satellite operator not all the satellite operator are okay. There are some questions. I don't know which type of answer. So you see in the chat, there is in the Q&A, the first one. So I don't know if you have some feedback. I imagine it's difficult always to find a balance between different positions.
Yeah, I can see the question. Yeah, from Tatiana, and yeah, she's saying that some operators supported, some still have questions, and what satellite components will be very soon approved. Well, what we are going to yeah, she's right. I mean, the concept, what we are going to approve is this report on the vision and requirements. So I think she's making reference to, as I said, the recommendation. The recommendation will not be approved soon. What we are going to approve soon is this report on the vision and requirements. With that, as I said, we are going to issue the circular letter inviting for the candidate radio interface technologies. And then at the end of the process, we will have this recommendation with the detailed specifications of the radio interface, interfaces. So this is not going to be, this recommendation is not going to be soon. We're trying to move fast, but it's definitely not going to be this year or even the next year. As I mentioned in the slide, it will probably by the end of 2024 or 2025. So this is the, yeah.
Okay, thanks. So there are many, so I know another question this is provided in another internal chat is about if a satellite broadcast is part of the EMBB.
Yes, definitely. It is part of the enhanced mobile broadband. That's in fact one of the, as I mentioned in one of the slides. So this is one of the usage scenarios or use cases within the EMBB satellite. We are definitely, as I said, I mean, defining now what would be the peak data rate and the user experience data rate. We are defining the final values for each of the terminals that each of the 3 terminals that we are considering. Yeah.
Sorry that I have not a good timer for the network. So I don't know if you answered this question. There are other questions. One is about the spectrum compatibility between the terrestrial and the satellite component.
Well, the satellite component, so this is a hot issue within ITU, but as you know, we have spectrum. The satellite component will definitely use the spectrum allocated to the satellites, more specifically to MSS, mobile satellite service, in accordance with the radio regulations. So the satellite component of IMT will definitely use spectrum allocated in accordance with the radio regulations to satellite users. So in particular to the mobile satellite service. So that's the idea. So I mean, this is a spectrum allocated to satellites. So the sharing or the compatibility is guaranteed by the general studies conducted within ITUR. But the band, we're definitely going to use bands that are formally allocated for satellite use in accordance with the radio regulations.
Nelson.
Yes.
A question, I have a couple. Is this IMT 2000 is taken care of some of the unconnected to the connected, and like in the applications for the remote area or the rural areas? How is it being done at this point?
Well, this is definitely under consideration, as I mentioned, and you can see in some of the slides. I mean, that's one of the main goals. So this is
Okay.
the complementary to the terrestrial, but mainly focused, as we say, to suburban and remote, as we say, unserved and underserved areas. And as you mentioned in your presentation, also aeronautical and maritime environments. So this is definitely the main goal of the objective of the satellite component of IMT 2020.
Okay, and another question is, how about these, the LEO satellite systems? There are thousands of them, they are planned, and there are various systems on the LEO. How is the spectrum is going to be affected with the IMT 2000 in any case? And if so, what are the issues on the spectrum issues, especially?
Well, as I said, I mean, being in non-geostationary or geostationary, we are going to use the spectrum allocated to the satellite. So those constellations, the non-geostationary or even the geostationary networks or non-geostationary systems, they will be using, I mean, frequency bands that are formally allocated to satellite service. I would say, in particular,
So
the
there's not
MSS.
much of an interference between the two that way.
Well, I think this interference it's managed by the sharing studies that we have conducting, and then some of them. I don't know if you, I mean, follow the discussions at the last WRC and continuing WRC, for instance, on the 2 gigahertz. So there are lots of studies and resolutions approved for the sharing and compatibility. So what I'm saying is that the fact that we are using those bands for IMT doesn't change what we are currently studying. So the use will be guaranteed through this all this sharing and compatibility analysis and resolutions and recommendations that we are developing to guarantee that.
Okay, so it must be one of the topics for work 2023 probably.
Yes, this is this is always one of the hot topics. Since I would say since WRC 07 is all this the sharing and the frequency bands, and yes, you are right. I mean, this is getting more complicated, but I'm always optimistic because we always find a solution, even with the adjacent band. Now we are not only talking about in-band sharing, but also adjacent band compatibility, which is becoming more and more complicated. But so far, we managed to find solutions, very, very technical solutions, which are reflected in these resolutions, ITR, WRC resolutions, and recommendations that we approve in the study groups for the sharing and compatibility. So I'm optimistic. I know that we are more and more sharing the spectrum, but we are always finding a solution for that.
The last question is, could we get a report on, as you mentioned, that you are going to publish this in September, so IEEE can get a member, I mean, as a report, as a liaison or something, which could be?
Yes, for sure. Yeah, for sure. In any way, the report is free. This publication of all the reports is free, it's publicly available. And yes, my idea is hopefully we are going to approve that in September, issue the circular letter, and then we definitely will push my colleagues to publish as soon as possible this report after approval. Yeah.
Thank you. That's wonderful. That's nice to see.
But I have a question.
Yeah, Zili, please. Yeah, it's your turn. Thanks.
This is Li Sang from Surrey University. In the past, in the satellite community, when we set up a performance indicator, we have a different parameter. For example, we call the advantage factor for the propagation delay when you evaluate the quality of the service. Do you think we should consider here, in the future standard, the performance should be have a different parameter with additional we call the advantage factor considered, rather than use the same parameter as the terrestrial network. You know, they have a latency of 1 millisecond or less than 1 millisecond. But for the satellite, I believe in the past many years, we do have a different parameter. Can you comment on this?
Yes, thank you very much. That's a very interesting question. Yeah, this is foreseen in the, not really now, but as you said, in the next phase for the development of the recommendation, yes, this is totally possible for the submission of the radio interface technology, and also for the evaluation groups, as you said, the evaluation phase. And so this new parameters, I would say, on new requirements can be definitely submitted to Working Party 4B, and then we in the focus of Working Party 4B, this can be discussed, and of course it has to be agreed by all the evaluation groups so that it can be considered. But definitely it is open. We are definitely open for that during the next, after the publication of this report, when we get into the phase of really standardization towards the recommendation. Yes.
Great. Thank you very much. Thank you.
You're very welcome.
Nelson, there are so many questions, so I think we will have a time maybe for other 2 or 3, and then I will ask you to answer typing also during the next. Okay. But there are other questions that are good. So I try first of all to compact 2 questions in one. The next question is: there will be a single device that will encompass satellite and terrestrial and on different services, and similar to related to this is a relation in the timeline between MT 2020 and MT 2030. So is there any
Yeah, that's very interesting. Another very interesting question. Well, that's, as I said on that handheld when I presented this slide. Yes, that's the goal. That's the goal. We would like to see one device, one user equipment capable of switching to the satellite or the terrestrial component based on the availability, on the best service, best quality that could be provided. So that's definitely the goal. And the second part of the question is also very interesting. I mean, 2030, yeah, that's, as I said, I mean, the main objective of this is 6G. Unfortunately, we're not yet there. We have not started in ITUR the standardization of 6G, but we are, as I said, trying to move very quickly to finalize the 5G. But I should say that, as you know, we are contribution driven, right? We work based on input contributions. So if during the process, that's now my wishful thinking, if during the process of development of this recommendation, I don't know, maybe in this process, we may start receiving inputs which for the 5G, which already may encompass some features of the 6G. So why not? We are open for that, to incorporate that in the development. So that is my really wishful thinking, that we could really accelerate that. Let's see.
Yes, so thanks a lot. We made so many questions to you. Probably I can select maybe there is another question. Maybe I don't know if it is too specific. Thinking about jitter impact in the recommendation, and if it will be elaborated on in relation to streaming. Jitter.
Well, right now, this is not being considered specifically in that point, but I may check the details and reply to that in a written form to that question.
Yeah, please.
Okay.
There are, some of them are more specific, so it's difficult to pose. I don't know if I missed some other, but I think these are the main points, so you can address
okay.
the other. Thanks a lot for your very, very exciting and interesting presentation. You gave us a view on the work of ITU, and this is really appreciated. And also this discussion is very interesting and gives an idea of the perspective of satellite and the standardization in this sense. So thanks a lot and very appreciated.
Thank you very much, Giovanni. Many thanks for the opportunity. Thank you.
And you will make available, I think, your slides. I plan to include your slides like the slides of the other presentation of the workshop, and then IEEE will handle in a suitable way. So I think, according to your, thanks a lot. So before handling to the first technical session, I think we have now the time for introducing a short presentation by the organizer Mohamed Slim Alouini of KAUST. That is, they will give in a short introduction of a competition for young scholar that is organized in cooperation with the IEEE FNI team. Thanks a lot, Slim, for being here, and I give you the floor.
Thank you very much, Giovanni. Do you hear me?
Very well.
Okay, very good. Thank you very much, Giovanni, for inviting me to the workshop in this particular session to try to give more information about, or actually, I guess not more information, rather kind of publicize more this event. So let me try to share my screen with you.
Yes, yes. I have also some slides in case, but you are more than happy. Yeah, you present yours. I've just provided in case, just in case.
I will not share slides. I will just share basically my screen.
Great.
Screen is about, because the main issue actually is an event similar to this one that's going to be organized in Riyadh, the capital of Saudi Arabia, in November. November 8 to 10, it's a 3-day event. It's an event that is organized under the kind of sponsorship or partnership between basically the Saudi Space Commission, the regulator, which is the Communication and Information Technology Commission, CITC, and ITU. This event will have a 3-day. The program is available in this. So the event kind of name is Connecting the World from Skies. Okay, so it's very clear what it's about. It's about satellite communication. Is about also aerial network, and here we're talking about HAPS and UAVs and things like that, and also the integrated aspect of ground, air, and space communication. This is going to be a big part of evolution of 5G and hopefully 6G. So the 3-day event is essentially some keynote speech as well as some panels, all by invitation. The program has been pretty much finalized. It's very much industrial oriented. Most of the speakers are coming from industry as well as from, like let's say regulators and ITU. So here you can go to this website, again, connectfromtheskies.com, and you look at the agenda. So day 1, day 2, and day 3. I don't think they put the name of the speakers. They just put the theme for now. Just to be clear, I am not an organizer of this event. I am just kind of a catalyst or someone trying to help making the connection with the academic world, because this has been essentially organized by the CITC, who have more connection and more ties with ITU and with the different, I would say, industrial active in the area of space and air. And they want to have this connection with the world of academia, and being professor in Saudi Arabia, they contact me to try to make this link. And because of that, we thought about launching this competition as part of a way to publicize the event among, in particular, PhD students and the young scholar. So this competition, again, it's described It seems that the link is not working anymore. I'm not sure why. Let me check here.
Yeah, I think one is working and the other has some issues, but one is okay.
No, it's working. Yeah, it's working.
Yeah, it's working.
The competition is very simple. It's open to all PhD or master students, as well as what are being called young scholars, people who finish their PhD basically between 2020, 21 and 22. So it's like roughly people who are 30 years old or less than that. Okay, and the idea is that the first author who has to be to be eligible, the first author has to fill that kind of requirement to be a student or to be a young scholar, and to submit by September 1st, a magazine-style paper that on anything related to non-trust network. So it's very wide. When it was discussed with CITC, they want to be very wide, which is exactly the theme of this conference, which means can be on satellite communication, but can be also on UAV communication, can be on the integrated UAV HAPS satellite, etc. So it's anything related to non-terrestrial network. And it's a magazine style paper, so it's not like technical IEEE paper, but rather, like we write magazine, which means it can have some technical content, but it's not about equations, it's more really concepts, the vision, perspective, maybe validated through some initial simulations. Okay, it can also have a demo aspect, a demonstration. This is actually also a possibility that can be included in this magazine paper. Basically, papers that has been already published are not eligible to compete, but if it's a paper that is maybe submitted under preparation or under review, so not accepted formally yet, the paper can go through the competition. Okay, the paper are not published, so the idea here is not to create a proceedings or to kind of compete with the IEEE Communication Magazine or Wireless Coding Magazine. It's just a way to kind of attract some good submissions, and out of this submission there will be a committee led by Giovanni and Dr. Al-Juhani from CITC, who will, so like technical program committee that will basically evaluate these submissions, and out of that, through a scoring system, the 10 top submission will be selected and will be invited to the event itself in November in order to present the idea in the form of this, as you know, like 3-minute type of presentation followed by a poster session. There'll be a jury considered by some of the attendees. There are some high-profile attendees by some of these companies like OneWeb, Starlink, and so on, that will attend this poster session by students, and that will basically present this to the jury, and the jury will then basically deliberate and select 3 winners. The first winner or the grand prize will get $5,000, and the 2 runner-up will get each $2,500. All the remaining 7 will be, of course, all invited, and the travel expense will be covered by the organizers and will be just called young. They will be recognized as young scholars for this particular event. So that's kind of in brief, basically what this challenge or IEEE competition is about. And if you have other questions, I'll be happy to take 1 or 2 questions.
Thanks a lot, Slim, for this very interesting and very stimulating initiative for young people to do research and to submit their ideas here. I don't know if you have some question. Thanks also for giving me the opportunity to coordinate the selection. I have no, at the moment, maybe there is one question from the panelists. I don't think so.
Very good.
So,
okay.
Yeah. We have one question.
So I'm going to share in the chat box the address of the competition, so that everyone can go and basically go and check for himself or herself exactly the details of this competition.
Yes. I will also, because this is for the panelists, I will also broadcast this
okay.
for, I will ask Matthew to broadcast on the participant. In any case, that's a great opportunity. So let's remind about the deadline. So when is the deadline to submit?
It's September 1st, so 40 days from now, roughly.
Okay, so that's people now participating, and still a lot here. So they have the time to think and to prepare this good submission. Thanks a lot for this contribution. And we now, thank you, Slim. We now have to handle to the next, because we have a tight schedule. We have to handle the first technical session. Now, that is, I introduce a physical layer for 6G non-terrestrial network. This is coordinated by John Bass, who laid this track. So I give you the floor, and you are now the session chair. Thanks a lot, everybody. And it's impressive to see how many participants we had today. So we hope that we provided a good introduction to the topic. And now it's a time to go into the detail. We have a physical detail today and quite a service after with another session. So John, it's your session now. Thank you.
Okay, now we are chair. Basically, the chair has 5 papers, and then the first paper will be presented by Manoj and will be the satellite 6G network, and then there will be more or less the use cases that we have. Then the second paper will be presented by Amita. Amita, that is come from DLR, and he's working with variable data rate, and he present optical communications. And the third part will be presented by Michele Zorzi, okay? And the fourth will be presented is the satellite roadmap, the physical layer. I will present that. And but here are other colleagues that has been done with me the paper, so if the work, so they can support. And also the final paper we presented by Melek, okay, from the KAUST, okay, on overview of recording, okay. So please, Manoj, you can start. You are mute, Manoj.
Yeah. Sorry. Can you see my screen?
Yes,
Can you see
yes.
my screen?
Yes.
Yes.
So, good morning, good afternoon, good evening to every one of you as your time zone is. This is talk about the 6G satellite network integration roadmap prepared by IEEE INGR working group for satellite. So I'd like to acknowledge the effort made by the entire reference architectures team, made it possible to arrive at this particular report. If I missed anybody's name, apologize. Now, so I will briefly mention about the reference architectures that we have come up with, that we have sized as part of this working group effort. Now, let me just give 1 second. Okay, so we have mainly considered the 6G non-terrestrial network for our third edition of the report. And this was done because of the evolution of the 5G as well as the deployment of 5G, and the whole community is moving over to the 6G requirements, 6G expectations. And while we are looking at what can be the key performance metrics or indicators of 5G versus 6G, while I'm sure that the 6G is very much under research and we are still not able to converge on what should be 6G, some of the early research indicate that very critical requirements on the delay aspect or latency aspect and inclusion of the jitter aspect and so on, which makes it very, very challenging for the satellite network to be used. But as the case is coming up with connecting the unconnected as well as connecting the rest of the 3 to 4 billion population, it is becoming imperative in getting the satellite networks to be integrated with the 5G as well as 6G network. So we have considered satellites of various kinds, LEO, MEO, GEO, and also for the case of highly elliptical orbit, among the orbiting units or orbiting satellites. And in addition to that, our reference architecture considered high altitude platforms which can actually be working above to 100 kilometers, and low altitude platforms that might be operating from something like 100 meters to 1 kilometer. So we can expect the latency of the order of microseconds, a few microseconds to fractions of milliseconds for this non-terrestrial units enabled by HAPS as well as low altitude platforms labs. So that is a representation of the 6 different types of non-terrestrial elements that we have considered. So this is just a motivation for how or why satellite can be considered for 5G as well as 6G communication. So this I just here considering different types of satellites as well as high altitude platforms as well as low altitude platforms for a quick comparison of a very simple round trip time estimation. So here we are considering a single satellite which is hovering a round trip time, say ground station to satellite to ground station. So as you might have already experienced very, very high delay for your satellites, we will be able to bring that round trip time to a couple of milliseconds for LEO satellites, which are actually very good candidates for 5G 6G services. So even with when you have a 1 millisecond switching delay at the satellite, we will be able to operate with the sub 10 millisecond time. If we consider a satellite cluster with multiple satellites, so here I'm considering like 3 satellites with up and down link communications, we still will be able to get 7 millisecond round trip time or latency, including 1 millisecond per hop delay as well as 1 millisecond per satellite processing time. Now, when it comes to 6G, when we use this high altitude platform as well as low altitude platforms, we can still bring down the delay, as we have to see that with the 3 hops and 3 satellite hops with the LEO satellite hops and HAP platforms, we will be able to bring that down to 7.5 milliseconds, 7.6 milliseconds time. Okay, of course, we may be able to bring down with a couple of hops the LEO as well as the low and high altitude platforms to a few 100 microseconds to few milliseconds. So there is a possibility for using satellites to achieve the kind of delay requirements. In fact, delay is one of the biggest constraints when we use the satellite network compared to throughput. Throughput may be easier to achieve, however, delay cannot be easily reduced. So that's why the integration of all the elements are very, very important to not only to reach the unconnected regions, but also to provide the kind of services expected from 5G as well as 6G. So this is an integrated picture for representing all the use cases in our edition 3 document. I'll very briefly touch upon some of the points, as the report is very huge, particularly on the reference architecture side. So there are two categories of use cases. One, where the satellite or non-terrestrial network element is used as a backhaul network. The other, the satellite or non-terrestrial network is used as an access network, where user equipments can directly talk. So we have in the report, we considered about 12 different cases of satellite used as a backhaul network for the 5G network. So one example use case is here, where the user equipment talks to a distributed unit or the distributed unit or be talks to the satellite through S1 interface and the rest of the network. So this is essentially replacing the F1 interface of the traditional wired or terrestrial 3GPP network. So this is one of the use cases. Another use case is for the integration of the multiple UAV LEO segments, while the entire thing is actually being used as a backhaul network. So here the base station or the distributed unit is actually using the rest of the segments as a multi-hop backbone network to reach the core network. So essentially, even with the use of the LEO as well as high altitude platforms, we will be able to bring down the delay to 1.2 millisecond, which very well be meeting the 5G requirements. So on the other case of use cases where direct access is involved, direct access is allowed through satellites. So we have considered two cases. One, the E node B or G node B is actually based on the non-terrestrial network element. So here there are about 36 cases considered for such possibilities, where we will be considering relay access as well as the services of E node B or G node B provided by this on NTN node terminal. Okay. So whereas E node B or G node B considered on the ground is handled by the services provided through satellite as a backbone. Now, let's look at a few example use cases. I will not be able to cover everything since, as you see, there are about 36 different cases. So these are some of the use cases involving NTN node, where a LAP, low altitude platform, is actually involved in the communication system. So, in these cases, we have considered a very innovative concept of federated as well as non-federated cases. And this is becoming very important in the future when there are large number of clusters and there are large number of service providers who are willing to start. So the importance is because without having federated satellite network, every service provider, say service provider 1 will have thousands of satellites, and maybe another service provider 2 may have equally large number of satellites. But the entire resource is managed and used by one service provider. All the communications to and from this interface will be essentially reaching the internet for terminating to the end user. So that way, the resources in each one of the service providers cluster will be underutilized. Whereas with the federated, one satellite service provider may be able to use the resources available on the orbit from other service providers. So it may be possible that one of the user interface communication can go through one cluster or one satellite service provider's cluster and terminate through another satellite communication cluster. So by defining these federated interfaces, we will be able to achieve significant savings in terms of low cost of operation, better resource management, low orbital cluttering, which we need to seriously worry about the future of satellite networking, and even higher access speed, because your user interface, maybe this user interface is actually belonging to service provider 2, and service provider 2 is actually here. So he may not have direct access to satellite from service provider 2, but he will be able to access satellite from service provider 1, which will actually improve the access latency or round trip time too. So that's very, very important to have interface standardization, billing or traffic management to allow this federated communication. So let me show another examples of use cases where, as I have mentioned earlier, the centralized unit or G0P or E0P is actually located here. So which will allow us to have very quick communications. That way the latency can be much better when you have NTNs used. So in this particular case, showing another use case where the G0B is not in the immediate lab platform, but in a adjacent lab platform. So lab platform doesn't, one doesn't have a G0B, but lab 2 has a a CU or G0B available. So in that case, you will be able to relay and you will be able to get a service with much lower latency. So similarly, it is possible that the G0B may be located in a high altitude platform, which might be accessed through an L2 interface. So the second set of use cases involving direct access is using high altitude platforms. So we have listed about 8 use cases where the high altitude platforms will give direct access and services to user equipments using a S0 interface, where this E0B or G0B will be located on the high altitude platform. So one of the advantages is that it will be able to cover much larger area compared to a lab-based platform. So similarly, multi-hop services for the G0B can be enabled through the combination of HAP as well as LEO satellite clusters. Now, for the direct access, we also have considered the excluded cases of HAP or lab platforms. Instead, we directly consider satellites which are visible to the users, and all use cases have been listed out. So this is one of the cases where the user directly talks to satellite and LEO satellite, and within the cluster, there are selected nodes that provide the service of G0B, and you may be access that service. So thereby, in fact, with the virtualization and network function virtualization possibilities, the G0B can potentially migrate. If you see, for example, if there are several users from this particular area, the G0B may be migrating to that area so that you will be able to provide better services. So we have given in the report about 36 use cases such that. In addition to the regular services of 5G and 6G, IoT has been supported in 2 ways. One way is that through 5G, 6G based traffic support, where IoT traffic is just like any other user's traffic. In addition to that, we provided a different service where physical layer aggregation or physical layer combining can be done by a constellation of satellites to support IoT. So there are about 6 scenarios defined for various possibilities of the LEO satellite constellation provides amplify and forward or decode and forward services with direct or steerable beam support. And so these are a very quick representation of that. In scenario A, we considered the direct access transparent payload where IoT sensors will be able to get services of a constellation of satellites, which will be able to do amplify and forward services, where the physical combining will be done at the gateway. So scenario A and C are similar, where scenario C is using steerable beams. And in scenario B, we will be using the cluster of satellites for doing decode and forward, where the combining of final data will be done at the gateways. So this essentially helps IoT devices to use very, very low power communication, where a cluster of satellites can be utilized. So scenario E for IoT physical support discusses about the terrestrial gateways that will be relaying the communication from the sensors. So these are IoT devices or sensors which will be communicating with the terrestrial gateway, and the gateway will be using the satellite cluster support to do the the amplifier and forwarding service. And scenario F deals with the HAP or LAP platforms doing the transmission to satellites or using the services of the satellites for combining. So we proposed 3 reference architectures, one for the near term in 3 years, other for the midterm 5 years, and the third for long term 10 years. And the reference architecture 1, that is non-virtualized 5G satellite networks. Reference architecture 2, separate virtualized 5G satellite networks. And reference architecture 3, proposed for the long term plan, is integrated 6G satellite networks. So let me very briefly take you through that 3 architectural possibilities. One for the near term, which is separate, non-virtualized 5G satellite network. So in this particular case, we have represented here the 3GPP, 5G core modules as a representation of the 3GPP 5G network. Okay, so the satellite network segment is actually shown here, which is actually being used as a backhaul service. Okay, this satellite provides backhaul services for carrying the 3GPP traffic. There is no virtualization expected or being done in the satellite segment. So the user equipments or radio area network will be using the interface S1 to talk to the satellite clusters, and satellite clusters will be carrying the traffic. All the traffic for the 3GPP interfaces N1 and N2 will be carried over the satellite to reach the ground station and then to the core network, evolved packet core network. So essentially in this short-term satellite 5G integration, we expect satellite to be used as a non-virtualized backhaul network. This is the simplest and what can be possible, because it will be able to quickly enable connecting the unconnected population. So the second architecture is for the medium term or mid-term, which we anticipate can be accomplished in 5 years or so, which will actually have the satellite to be considered as a virtualized network, following the EPC kind of core for the utilization of NFV as well as SDN with the appropriate modules. So there are 2 modules that are very important as per our committee's discussions. One is satellite edge computing function, SDF, and the second thing is satellite network federation module. So these 2 functions are new functions which will actually make a significant impact in this satellite virtualized network. And the NFV management and network orchestrator module will be responsible for providing all the network management, the resource management, and the kind of services management of the entire network. So now, we have 2 different virtualized but separately virtualized network here. The 5G 3GPP network here, and the satellite network, which will be virtualized, but it's separately virtualized. So the interface between these 2 networks will be managed through an M1 interface that is between the management and network orchestrator modules of each one of these networks. Now the third, module, so the third reference architecture. So the orchestrator or mano module is expected to do the critical functions such as flow management, end-to-end resource management, including routing, resource orchestration, network service orchestration, scaling functions, and automation of various functions over this NFV and SDN framework. So the reference architecture 3 deals with long-term integrated 6G network control plane. Okay, so this is having a single virtualized EPC, which will be having all the existing 3GPP network functions as well as additional functions like network, satellite network federation function as well as satellite edge computing function to do a global management. So this essentially means that as a user connects either in a user equipment, either is directly connecting to a ground station or through a satellite. And his communication services in the satellite segment also will be managed by the service provider. So this is actually the true integration of terrestrial as well as the non-terrestrial network as we anticipate in the next year. So we have also reported major architectural needs for various possibilities. One, new integration architectures in order to meet the traffic performance. Federated networking I have already mentioned, and 5G MANO to satellite MANO interface, M1 interface definitions and creations. And we also want new satellite network interface definitions needed for 5G satellite. S1 interface I have mentioned, which is defined for UE and LEO satellites. Similarly, S2 is also to be developed. So in the long run, we have several open research problems that need to be addressed in achieving the goals of this architecture. So the major challenge, all these requirements or needs are also major challenges because they are not existing as of today. So as I mentioned, they are integrating the network, achieving the latency performance through this integrated network, and to develop the interfaces, to develop the M1 interface, and to develop virtualized satellite network. And also the 10-year framework, we need to develop the integrated MANO module, associated service functions, and the network interfaces. So one of the important aspects is that new services can be hosted in this migrated dynamically based on the needs. One specific service, in addition to IoT and many other services mentioned, is space-based hosting service, which is essentially to have the entire web hosting or content hosting done through the satellite clusters. So this is essentially important because the population, in rural areas and unconnected areas, even though they have communication, they may not be able to access content that they really need. And it is possible that the content can be located in a couple of 1 to 5 milliseconds away from them, no matter where they are on the earth. And this can be achieved only by placing the content hosting servers on the LEO clusters, which can be periodically updated by the backup data from Geo or other kind. So you will be able to get substantially lower delay to deliver contents on that. So with this, let me conclude. So we mentioned about the reference architectures from the roadmap document, edition 3 of the roadmap document, which deals with the near-term, mid-term, as well as long-term requirements of 5G, 6G satellite integration. We have discussed the major use cases, which covers 2 categories: backhaul access category, direct access category, and we also mentioned the physical layer support required for IoT traffic. So the 3 reference architecture: 1 for near term, reference architecture 2 for the mid term, and reference architecture 3 for long term were discussed in the report. And the report also highlights major needs and challenges, opportunities. These are actually a good source of open research problems for the community. So feel free to take a look at that if you are a researcher in this area. So yeah, let me conclude this. If you have any questions, feel free to ask.
Manoj?
Yes.
I have a single question. It's an excellent presentation. You gave the architectures as usual. It's good, but the one thing is about the latency issues. If we consider from most of the example which you showed some on the 5G, or if you extend that to 6G, between any of these, either 5G or 6G, still the latency from this from the architecture's point of view, if you can tie with applications, I think that you already mentioned one or two in the last couple of charts.
Right, correct.
But if you can identify some applications which is useful from the delay point of view, say one of those caching in the rural areas, which you mentioned in one of the previous charts, that is a good one. Similar to that, if there are more applications which you take out and then map to those architectures, to those things, I think that will be another. Do you agree with that?
Yes, I absolutely agree with that. So, in fact, the example that I have mentioned earlier, assume about 3 hops of satellite, inter-satellite links, where every hop is actually adding 1 millisecond delay. Okay, that is able to give sub 10 millisecond round trip time, including what is it called? The propagation delay, switching, and other kind of delays, which is giving us very big confidence that we'll be able to achieve, sub 10 millisecond delay for 5G standards. So, if you want to give content access to the users, which can give sub millisecond delay, that may also be possible. So, I was just trying to bring this particular. Yeah, this is where I have found it is possible that sub 10 millisecond delay can be accomplished even if you have 3 satellites and 1 up and 1 downlink involved, where you have 1 millisecond switching available with everything. 1 millisecond switching is fairly good for most of the traffic group, most of the satellites. We may be doing much better than that. So, so we can further do that. Even a couple of milliseconds can be done if we can host the content on the cluster itself. If the content is entirely on the LEO cluster itself, so we'll be able to bring much better. So our architecture allows that because we defined satellite edge computing as one of the very important functions of 5G satellite integration, and space-based hosting as one of the applications of 5G satellite integration. So it is definitely possible to accomplish 5G delays and probably 6G delays too.
Right. And another question is, you have 2 different services, O3B and the other one.
Perhaps we have to reduce the time because otherwise.
Yes. This is the last question. There are 2. O3B and others, they federated, where they can access between the 2. But is it going to be that is ideally it is a good situation, but practically maybe something that's one we have to think about it.
Actually, this is that's the reason I mentioned Shastri, that this requires a lot of research. In the next 5 to 10 years, a lot of students will be graduating in this area because a lot of problems are to be solved. So, but it is possible. It is possible in the sense that we see the evolution of 5G to 6G, the possible performance enhancement that we are anticipating. There will be significant need for integrating with the satellite segment too. So, as a result, I assume there will be significant interest from the researcher side that will reflect on the realization too.
Yes, thank you.
Thank you.
So,
thank you.
Okay, thank you, Manoj. Very interesting presentation. So for the next presentation, it's Amita, but I don't think that if Michele has problems with the time. Michele?
Yeah, I'm here. So
you have problems with the time? Or
no, I was asking because I thought the session was starting at 1, and it was a talk every 20 minutes, and so I was up next. But there is another talk before, so I just have to leave at 3 because the session was supposed to end at 3. That's my only constraint. I'm happy to go after you in 20 minutes.
Okay. Yes, Amita, we spend 20 minutes more or less. Can be here 20 minutes more or less?
Yeah, sure. No, for the talk, I see no problem for the talk. It's for the last part of the session, the round table, which I probably have to leave.
Okay.
All right then.
Yeah.
Okay.
So Amita, please, you can.
Yeah, thank you, Juan, and thank you very much for the opportunity to present this topic in this community here. Can you all hear me and see my full screen? Can somebody give
Yes, Amita, yes.
Thank you very much. So, yeah, my name is Amita Shrestha, and I work in German Aerospace Center in Germany, in Munich, in the Institute of Communication and Navigation. Today, I will talk about a little bit different topic, it seems, that we have in this round. So I will talk about the variable data rate techniques for optical low Earth orbit downlinks related to free space optical communication. So just wanted to quickly introduce very fast where I work, and I work in the Department of Optical Satellite Links in Institute of Communication Navigation in DLR, as I mentioned. So we have 5 different groups. We are focusing on the free space optical communication, and we work on the development of the optical communication terminals and also the ground stations, as you can see also in the pictures. We also work on the study of the channel and on the high throughput optical systems and advanced optical technologies. And since last couple of years, we also have a group working on the quantum communication systems. So just a brief introduction before I dive into the topic. So today I will, this is the outline of my talk. So I will give a brief introduction about the free space optical communication in general, focusing on the LEO to ground link. And then I will talk about the motivation of using the variable data rate techniques for particularly these scenarios, detailing on different modes that can be used and different topics that we are working on. And then finally, I will conclude my talk with a summary and outlook. So free space optical communications. So it basically consists of different scenarios, starting, going into the deep space communications and near Earth relay communication with inter-satellite links or with the satellite to ground links, and then also direct to Earth LEO downlinks. This is the main topic for today. So I will focus only on the optical LEO to ground link. I think most of us are aware what are the advantages of FSO. So we are talking about 6G at the moment, talking about very requirement for the very high data rate. So this is one of the, let's say, biggest advantage of going free space optical, because it can provide very high data rate, low power consumptions. Since this is a direct line of sight communications, it has a high security, as any eavesdropping would be detected, and so far no spectrum regulations for this reason of the spectrum. So now just to give a brief introduction on how typically the LEO downlink scenario works. So as we know, the LEO satellites are orbiting around the Earth in the LEO orbit, which the distance altitude of the orbit varies from 160 to 1400 kilometer, let's say. And typical LEO orbit, as we all know, is ISS, which is about 400, almost 400, between 400 500 kilometers from the Earth. And so we have a ground station on the Earth somewhere, and then the satellite moves around in the LEO orbit, and after some time, when the satellite is above the horizon, typically 5-degree elevations, we have a link acquisitions between the satellite terminal and the ground terminal, where the signals are acquired, and the tracking, continuous tracking, and data transmission, or let's say the communication is done. And finally, when the satellite moves below the horizon, the link terminates. So for typically the LEO to ground link, we have about 10 to 15 minutes, depending on the orbit, for the data downlink to particular ground station, let's say, at that particular time. Now, of course, nothing comes for free, so there are quite many challenges for the free space optical communication, and one of the biggest challenge is turbulent atmosphere, which causes the scintillation and the fading. So as we can see in the figure here outside, let's consider the satellite to ground link, where from the satellite, the signal is transmitted, which is in the form of the very nice Lie-form Gaussian beam, which travels through the atmospheres. And the atmosphere is that is causing trouble is around 20 to 25 kilometers above the ground station, where we can see there are different IRT cell, which has different refractive index, and that will refract the beam and will cause lots of turbulence and scintillation that will cause the fluctuation in the amplitudes and phase of the signal. And what we receive at the ground station with the telescope is not anymore Gaussian, very nice light, but it is distorted. So this is one of the biggest challenges. Another challenge is, of course, the fog, rain, snow, haze, clouds that causes the fading and link outages, because, of course, the free space optical communication is a line of sight communication. Another challenge, which is, let's say, a little bit easier to tackle, is pointing and tracking error. So it depends on the system how accurate this is, since the FSO communication is a line of sight communication. Very good pointing and tracking is very important. Otherwise, simply we lose lots of information. Of course, there are lots of studies for the mitigation techniques for those challenges. Easiest or hardest, let's say, the solution is to have the bigger telescopes, which causes the aperture aberration. And yeah, if we have very big telescopes, then these problems, most of the problems can be solved. However, this is not always possible. There are also studies on different adaptive optics techniques, complex post-processing of the optical signal, and one of the solutions that we are working on is simply variable data rate, so operating at different data rates according to the channel conditions. So just to give an example how the signal looks like, I just took one of the experiments that we did in 2006 and 2009. That was a laser communication from the Japanese satellite called Kyoto experiment. Just to give an example how the signal looks like, this is optical power that was received into into our telescope at that time, which is 40 centimeter in diameter, and we can see in the figure here, the y-axis is the power received, and the x-axis is the elevation from the ground station to the satellite as the satellite moves in the orbit. I mean, you can see there are some jumps down. This is mainly because of the tracking error, but most interesting thing to see here is how the power varies with the elevation. As we can see here, at lower elevation, we are receiving lower power, and we will also see that we have a higher scintillation there. This is mainly because the signal passes through the atmosphere for a longer time when the satellite is at lower elevations. And that the situation improves, or channel condition improves, as we go higher with the elevations. This is just to show like excerpt of the signal received, how the signal is fluctuating. And as I was talking, scintillation is actually measured as how much the signal is fluctuating from the mean power. And this is one of the important measuring index, let's say, to understand the channel. And this is just to illustrate how this scintillation index varies also with the elevation. These are the plots for different experiments done. And as we can see, without going too much in detail, that at lower elevation, the scintillation index is quite high. So lower elevations are quite challenging. The question is, can we skip the lower elevations? And this is mainly the approach that is used just to start the communication at 20 degrees. This is very typical. However, what does it mean that we are skipping the lower elevations? So thankfully, there were some study done to understand how much we are losing if we start at 20 degrees, for example. This figure here shows for a certain scenario, what is the probability during this link time that the elevation is below certain degree. And if we are now talking about 20 degrees here, we can see that we are utilizing only 25% of the link time, which is quite much because in one pass we have 10 minutes. So we are losing 75% of the time where we could use this time to download many data. So actually, it is very important that we start earlier, and if possible at 5 degrees. This is our goal, to really start the communication at 5 degrees, which means we have to solve the challenges of the difficult channel atmospheric issues at lower elevations. So yeah, the lower elevations are challenging, but it is very important to maximize the available link time. So one of the solutions that we are working on, among other solutions, is instead of just blocking the transmission at lower elevation, just doing it, but at the lower data rate. So this will improve the overall throughput of the link. So here to illustrate what does it mean, so how much data rate variation we would need to do for typical LEO to ground link. For example, here if we start at 5 degrees, in order to achieve the maximum throughput, and the data rate variation of already 25 times is required. And this is only considering the atmospheric attenuation. So it's not considering the scintillation effect. And if we extrapolate this graph, the scintillation would move this graph, and the data rate variation required would be even 100 times. So this shows kind of the motivation why the data rate variation is important to let to maximize the link and start the communication already at lower elevation angles. So now, after the motivation, I would like to move on what are the different modes where we want to vary the data rate for satellite to ground FSO links. Sorry, it's a little bit not so responsive. Okay, so one of the first mode is simply, especially for the ground station, to support a different satellite terminal. As we know, with the time, there are different FSO terminals on the orbit, and we do the experiment with different satellites with our same ground stations. And in order to avoid the problem that for each experiment we would have to change the whole setup, it's very important that the ground station supports simply different data rates, so that for different missions and different experiments, not so much new work is to be done. So this is like a very simple mode where the data rates are just changed for different missions with different terminals. Another mode would be static during the pass. So in order to simplify the system, not changing the data rate with each elevations, but for one particular link between the satellite and ground, the optimum data rate is chosen, and then it is fixed. So it is designed for different transmit power, depends on the system design, passes and beam divergence, and etc. To make it more fruitful, which is more interesting, is to make it dynamic. So the data rate really varies during one pass. As we know, at lower elevation, the channel condition is bad. So we start at 5 degrees with very low data rate, and then keep on increasing with the elevations. This can be also done at different complexity level. One could be variable and pre-programmed according to elevations. Since we know the orbit information of the satellite, we know the timestamps at which what will be the elevation at which time. So the data rates could be pre-programmed just to tackle different elevation issues. It could be also adaptive without uplink channel by depending upon the channel state information, because as we know, we will have a beacon signal. So the beacon signal also kind of give you an idea of how the channel is. So this can be used to kind of adapt not only with the elevation, but also directly with how the channel condition is. And another one is, of course, most sophisticated one with the direct negotiation between the ground terminal and the satellite terminal. So this could be 3 different modes. And talking about different techniques, so we investigated different techniques, how we can vary the data rate. So there were 2 branches, let's say. One would be to change the user and the channel rate as well. So another would be only varying the user rate, so not changing the channel data rate, and this would be used for the fading mitigation. So for using really changing also the channel data rate, we'd have to vary the modulation or the type or the order. This is very common in radio, let's say. And for the other option to just vary the user data rate, keeping the channel data rate, there one could vary the FEC protection and also the interleaver size depending on the channel. And other 2 options that we are working on, also similar to interleaver, is delayed frame repetition and code word spreading. I will quickly mention it because I think we don't have time to go in detail. So variable data rate by varying modulation. So this is, I try to explain it in a very simple way. It's just changing the since we are mainly working in the on-off keying, so domain non-return to 0. So this can be achieved by just changing the length of the pulse on the receiver side, so that longer the pulse, the lower the data rate is. However, this requires the change in the receiver hardware, but it's a low complexity. So another option is to vary the order of the ppm. This would work better because then the pulse length is not changed. This would avoid that we need to change the receiver hardware or filtering, and it also provides the better receiver sensitivity. However, this is higher complexity, especially if we want to vary the data rate during the link for different elevations. Another option is to move from non-return to 0 to return to 0 and keep the length of the pulse by changing the duty cycle of the return to 0. This, with the simulation, this has shown that the receiver sensitivity remains constant and it works better than the first option. And another option I talked was about delayed frame repetition. So this is touching the other side without changing the channel data rate. So the channel data rate will be still high. However, the user data rate will be changed. So just an example, let's say we have we have a frame, and the idea is just to repeat this. So it's like a repetition coding, but to repeat and send it after certain delay because of the way the free space channel is. This is the excerpt of the real measurement here, and I just wanted to show, if we zoom like some part of it, we can see like at some instant of time, the signal is below the threshold, let's say, and it falls into the fading region, and after some time it is way above. So the signal is fluctuating so much. So idea is to do the repetition coding, but to send this repeated frames after delay of around 10 milliseconds, typically, which is like a fading length of typical FSO channel. So so we did the simulation for different channels, and this concept also add a redundancy, of course. Therefore, it is only advantageous if you do it for a more challenging channel with higher PSI, let's say, that will obviously cause longer delay. Another concept, I think the last slide here, is code word spreading that we are working on, is also similar to, you can call it like a block interleaving or so. So there the idea is, of course, there will be a forward error correction scheme because this is one of the way to get rid of the noisy channel. However, since the fading of the FSO channel is so long, it will affect the whole code word. So we will anyway lose the data. So here the idea is, instead of completely repeating the frames and sending it, that will add more redundancy, is to split the code words. So instead of just repeating it, is to split the code words into 2 parts. Let's say, for example, for this one, we have like code word 4, 5, and 6, and K. Let's say systematic code with half rate, just for example. And this code word is split into 2 parts. For example, the code word 4 is split into 4A and 4B. And similarly, the code word 5 and 6. And the idea is just to send them, separate them, or interleave them, so that the first part of the code is arriving earlier and the second part after. This is mainly interesting for the systematic codes, because if the one part of the code is under fading and we don't receive, we can still recover it if the other part of the code is in this good channel condition, and the signal can still be retrieved. So this is the concept we are working on for the Leo to ground links. And yeah, this already brings me to summary. The main idea is to vary the data rate to guarantee the link with different setups, or one pass with varying link budget, considering the low complexity. Of course, there are other ways to cope with it, adding different sophisticated coding and interleaving techniques. However, if you want to design a system, not adaptive system, already working at lower data rate, that would just require more resources also when it is actually not needed. For example, at higher data rates, the channel condition is very, very nice. So we talked also different techniques, just briefly introduced by varying different modulation order, or increasing the length of the pulse, and delayed frame repetitions and code word spreading. The goal of this topic is to identify and optimize the beneficial methods for variable data rate for this scenario, with a key point of keeping low complexity, because this whole topic is driven with low complexity and low cost. And the outlook here, so since free space optical communication is also gaining lots of interest, and so we are involved in the standardizations, so space standardizations for optical on-off keying, free space optical Leo downlink, and there also we consider the variable data rate approach with low complexity. And yeah, so we are working on it, and also the outlook is to, so since we do also quite some experiments and develop our own satellite and ground terminals, is to not only limit to the simulation, but also to implement it, and yeah, and then verify the techniques and in the real experiment. So this would be my end of talk. Thank you very much. I hope it was interesting, and if you have any questions or queries, I would be happy to answer. Thank you very much.
There's a question, and that is, you have been working on techniques for the uplink of LEO satellites.
Mm-hmm.
Because you present results for the downlink. You have any results or any technique for the uplink of the LEO?
For the uplink, we are working on it, but I don't have any results here to present for the uplink. Yeah. So obviously for the uplink is more challenging. So we work with the lower data rates in the uplink. Yeah. But I don't have some results here for the uplink because this topic was focused for LEO to ground downlink scenario.
Can I follow up this question, please?
Yes, please.
Because just your question, you said the uplink is more challenging. Do you know why uplink? I thought the downlink is more challenging because the satellites rely on the solar power, and you send on the ground you can have more power, more facility. You can make it more power there.
Yeah. So first of all, thinking from the how do you say, from the atmosphere point of view. So for the downlink, the satellite sends the signal, and the atmosphere is closer to the ground. So the optical signal is diverging, let's say, and then when it reaches the atmosphere, it's quite diverse already, and the effect is compared to the uplink less. Whereas for the uplink, the signal directly passes through from the beginning through the atmosphere, and then they are already like spread it, and then it diverges and until it reaches the satellite. It's very the atmospheric effect is very high. So that's from the atmosphere perspective. It's very very challenging there. And what you said is true, that on the satellite it's more expensive and so on. That's one of the reasons why, because all the, for example, on the ground we can, it's cheaper to make, let's say, bigger telescope. So, but to receive the light from the larger distance. However, on the satellite side, for the uplink, they need to, it's very difficult to make the larger telescope. So that's why, that's one of the reasons. And it's always like also thinking from the decoder perspective. So all these coding techniques, they are very, the encoders are very, very simple. However, the decoders are made very complicated. That's why all the resources can be used on the ground stations. So the receiver on the ground is always easier, let's say, on that perspective as well.
Okay, thank you.
Many thanks, Amita. So now we give the floor to Michele Zorzi.
Okay, thank you very much. Bye-bye.
Okay, should we be able to see my screen?
Yes, Michele. Yes,
okay.
Go ahead.
All right. Okay. So, hi everyone. This talk is about some issues of non-terrestrial networks for 5-6G and trying to identify some relevant trade-offs that appear when we consider these scenarios with the available or foreseeable technologies here. Now, the inspiration for this area of research came from one of the 6G use cases. You can see here a few of them, which is the one in the middle, worldwide connectivity, because there is a desire and a push to make sure that connectivity is for everyone, not just for a few people. And if you look at the numbers, we have a problem worldwide because, as we consider connectivity like a commodity and we take it for granted most of the times, sometimes we don't realize that there are 3 billion people in the world who are unconnected. And of course, these people would live in remote areas, rural areas, maybe in countries where the economy is low, and in parts of the world where development is struggling a little bit. But the reality is that these people miss out on the opportunity to enjoy, not just for entertainment, which seems one of the main applications here in our countries, but opportunities for life improvement, for jobs, for education, and to access, better quality of life in the long run. And knowing that, a large fraction of the people in the world are not able to access those opportunities is, a humanitarian tragedy in a way, and something we should think about in order to solve this gap and try to provide this more globally. In fact, if you look at some of the numbers here, but the numbers themselves are not very important. The essence of the message is what I said. And just so we don't only think about developing countries, I have data for Italy, but I'm showing here data for the US. If you look at the US, there are places in the US where connectivity is actually quite poor. And so even in the US, where high-speed internet access is almost ubiquitous, if you go to some states or some counties, you can have issues. Maybe it's not so interesting to provide connectivity in some areas which are deserts, even though some people live there too. But there are other rural areas where a significant number of people may be underserved. And so clearly there is a need not only in some specific countries, but even in what we consider to be the developed world, there are people who are far from connectivity. Now, clearly, to provide this connectivity in those disadvantaged areas has a cost. The traditional way to provide more connectivity, which is to densify the network, may not be economically feasible. It may be even technically difficult because those areas, being remote, pose challenges in terms of electrical power supplies. Also, it becomes difficult to maintain those networks, and the economics also of this operation may be unfavorable, so that there isn't really a business case for a commercial operator to go and deploy the network. And so traditional cellular networks have some difficulties there. And so, if we want to provide the internet and Internet of Things everywhere and make it become the internet of everyone, not just all things, but all people, then there are some steps that need to be made and some gaps that need to be closed. Now, in addition to that, the problem of connectivity exists in traditional networks, even in 5G, in some specific cases. So I'm showing here one possibility related to natural disasters, where some unfavorable events, and unfortunately, they're becoming more and more common these days. This event may quickly compromise the infrastructure so that large regions may remain without connectivity as well as electrical power. And so having a means to compensate for this lack of infrastructure clearly is valuable. Also, we experience problems with the crowded areas. So, if we don't want to look at natural disasters or war events, which are also common these days, unfortunately, we can think of happier events like big concerts or soccer games, where we have a large density of people only occasionally. So this doesn't justify the deployment of a permanent infrastructure, but clearly calls for some ways to provide bandwidth on demand in some specific areas. And so these are issues that are there and should be solved, addressed creatively by using a mix of technologies. Cellular networks by themselves clearly are not going to be the answer for this issue here. Now, non-terrestrial networks play an interesting role here for a couple of reasons. One is that 5G is essentially a two-dimensional system, and
Michele, could you
yes.
maximize Could you maximize the screen? Because I think that you have not maximized the screen.
I actually see the whole slide on my whole screen. I don't know.
Oh, okay.
So do you see it cut?
Yeah, seems it cut, but in any case.
Which piece? Yeah, sorry about that. I don't know how to do that.
It's okay here.
Okay. All right. So one thing is that 5G networks are essentially two-dimensional, and except for maybe downtown areas with high-rise buildings, but these are just a few tens of meters, not really three-dimensional per se. But we start seeing a lot of flying objects and needs for connectivity also in the third dimension. And so 5G is not designed for that type of connectivity, not only because we may have terminals at some significant distance from the ground, but also because the network infrastructure can actually be deployed three-dimensionally, which gives interesting possibilities that we can explore as in terms of use cases and also some performance improvements. In addition, related to the soccer game or concert use case, the problem there is the tight coupling we have in current systems between relays or base stations, G0Bs, and so their location and their coverage. So these two things are essentially the same, right? They're tightly coupled, and this becomes a weakness as soon as you have a peak of traffic in a certain area and you don't have base stations there or not enough. Now, what is interesting in non-terrestrial networks is that you can decouple this thing. You can decouple the actual location of a node from its actual coverage by using spot beams and leveraging on this distance of the node from the Earth, which can play around with adapting the coverage where it is needed. And so this provides an interesting infrastructure which goes beyond this limitation, which in some cases may become quite strict. And in this picture, you can see a number of scenarios and possibilities. Some of them have been mentioned also in previous talks. So there are just relaying possibilities, and you have large coverage of rural or sparsely populated areas. You can have disaster relief when the infrastructure is compromised. You may also have these nodes not just as relays as in traditional satellite systems, bent pipe or even regenerative, but just pushing bits up and down. You can also provide services in the air. You can have edge computing type of applications in drones, in HAPS, in satellites. And according to what you have available, you can provide services and you can improve the performance in some scenarios. And we'll get to that in a minute. So I'm listing here 3 technologies that we examined. So technological trends which relate to this area and characterize, a push for 5G and beyond and 6G. One is certainly a spectrum issue, which has to do with the use of millimeter waves. Now, millimeter waves are interesting because there is a significant chunk of spectrum which is available at those frequencies, but they have issues related to propagation, especially in terms of large attenuation and blockage. So we need to solve those issues if we want to make it work, make the system work. And this is even more serious when you involve satellites because of the distance, right? So attenuation goes as the square of frequency. And so if you go from 3 gigahertz to 30 gigahertz, there's a 100 factor or 20 dB factor of attenuation in addition. And given that we operate on large distances, it's a legitimate question to ask whether we can even close the link at those frequencies. So the first question was, can we actually make it work? Can we have enough signal at the receiver using all the techniques we know in terms of beamforming and also using some accurate channel model, which takes into account not only the basic terms that we're used to in terrestrial networks, like the path loss due to distance and building entry loss, but also some phenomena that occur in the atmosphere, which can be ignored and are usually ignored in terrestrial networks, but become important in a non-terrestrial network and at certain frequencies. And so by working, the math, which is actually very easy in this case, it's a back of the envelope calculation, we can get a sense of whether this link can be closed and what is the available capacity we can achieve, just to get an idea of what kind of service level we can expect from the systems when using millimeter waves. The second technology trend has to do with the multi-layer architectures. These also have been mentioned in previous talks. Now, the baseline is the direct link from a geosatellite to a ground user. Okay, so that would be, and that is difficult because the distance is large, and with millimeter waves, of course, we have the attenuation issues I was mentioning earlier. So one way to mitigate this problem is to use intermediate nodes where we break the link into two links and we regenerate the signal. And so we can expect that this should work better, but we have multiple options. Right? We have maybe a LEO satellite in between, or we can have a HAP, a high altitude platform, or we can have both. Now, this scenario brings in several interesting considerations. First of all, where is the optimal breakpoint? That's not obvious, as we will see. Second thing is that if in the previous study, when studying the link performance, we looked at one point-to-point connection, here, as soon as you have an intermediate node, then you have a multi-hop connection. And so the way to compute its performance and the way to optimize the performance is actually different and depends on many different parameters that belong to the different nodes involved, including the one in between. Okay, and so it's not obvious that what intuitively would seem a good solution is actually the one you would choose when you go through the optimization or a careful study of what can be done. The third technology is, as we mentioned earlier, edge computing, which provides services in intermediate nodes in place of processing all the data locally in the generating nodes. So offloading data to a more powerful node, get it processed there and get it back as a result is a paradigm which has become popular these days. And here, having multiple layers and multiple nodes at different distances and with different capabilities, the question arises of where you should place these functionalities and which is the most favorable choice, which may depend on the application and other parameters, but the trade-off is there. And it's quite obvious, in fact, that if you go higher in distance from the Earth, you usually have more powerful nodes, from drones to HABs to satellites. And so you would expect a capability in terms of computation, which becomes higher. And therefore, the processing time becomes lower correspondingly. But then the communication time is instead higher the farther you go from the Earth, because you have a larger distance to cover, and you may have multi-hop connections, which take more time. And so, when you move the computation farther away, you are encountering this trade-off because you expect higher computation and so lower processing time, but you expect as well longer delays and therefore latency. So where is the optimal point is also an interesting question, and designing the system or making those choices according to multiple constraints and multiple objectives is definitely an interesting study. So these are three directions in which we have explored. And initially what we did was to identify the main trade-offs, very simple. So no fancy models, no complicated simulations, no measurements, just basic models for propagation, basic expressions for the Shannon capacity, and just outage probabilities, and try to understand, where these trade-offs arise and how they can play as a first step towards, of course, more accurate studies and more realistic studies, which will come later. Just to give you an idea of the type of results we obtain, here are one example for each of the three areas. So this is a trade-off between the antenna gain, which can be achieved, the frequency, and the capacity that results. Now, as you go up in frequency, you have more bandwidth, so the capacity increases, but also as you go up in frequency, your propagation becomes more limited. And so there is this trade-off which at some point kicks in. And so this curve does not keep increasing because at some point, as you go higher in frequency, you start coming down, okay? And so that's one trade-off which is interesting and should be understood properly. In terms of antenna gains, of course, the more the better. Obviously, 200 is absurdly high. 100 still on the high side, but even on with reasonable numbers, you can achieve a few gigabits per second of capacity, even on a geo connection, which is quite long. And so the question of whether the link can be closed has a positive answer with all the caveats and all the optimizations that may need to be in place. But this is what we have. Now, to the right on this slide is a performance graph that compares different architectures. GE is the direct geo, GLE is the geo with the LEO in between. GA, we show performance in two dimensions. One is capacity, which is on the horizontal axis, and the other is outage probability, which is on the y-axis. You want to be your outage, and you see that if you compare, the LEO in between is actually does quite poorly. It's just as not having actually, and so from this study, the HAP relay seems to be the most promising solution. I must say that this was done based on published 3GPP parameters for LEOs and HAPs. And our observation was that LEOs in 3GPP configurations are quite at a disadvantage compared to other nodes because the antenna gain, the transmit power was assigned to them is actually quite low. So they may have their own reasons for that, but we recognize that this configuration, which is punishing the LEOs, make the LEO solution not very attractive in this case. But this is just an example, and many trade-offs actually have been studied in the papers and in the slides. You have references to the papers we published in this area, and so you can find there all the detailed trade-offs with elevation distances. Many studies that give you more information there. Finally, for the edge computing scenario, here we compare the local processing, which is the red bars, versus the offloaded HAP-assisted edge computing, which are the blue bars. And this is the latency, the total latency, communication plus processing. And of course, you can see that local processing is taking more time because of the limited computation power of the vehicle in this case, whereas the better, and this depends on how many vehicles we have, because the more vehicles you have, then the computation at the HAP becomes a bottleneck, and so you get more latency in that case. Here on the right, we're comparing this as a function of the computational capacity of the vehicle, the ground vehicles. So if the computational capacity is low, then the local processing solution is unacceptable, it's even unstable in this case. But then as the computation capacity goes up, offload probability, which are these gray diamonds, becomes lower, meaning that more and more vehicles will choose to perform the processing locally as opposed to offloading to the HAP. And so just an example of the type of trade-offs you can study here, and the type of results that you find, which are quite intuitive, but it's interesting because we can characterize this numerically once we have all the parameters that we need to characterize the system there. And so to conclude, just a few open challenges. So we need channel models for these ground-to-air channels, because this is not as well studied as in terrestrial networks. We need means to coexist with the spectrum, because as we go to millimeter wave, there are many other services that are there in the satellite world, and we don't want to conflict with them. We want to find ways to coexist, but research has been done in the past couple of decades on connected radio and things like that. And so we have tools to deal with that. There are a lot of physical layer issues. The use of TDD, ARQ for long latency links, synchronization in large cells. And so there are things that need to be, and also waveform design for this kind of persistence. There are also issues related to initial access, channel estimation, directionality, how to recover from a link failure, and things like that, how to search in a cell. We need to manage the constellation if it's not geo. And so there we have to manage handoff, but this is quite well-studied subject. Plus the mobility here is predictable, and so it's easier to handle in general. There are many architectural issues like software-defined networks, how to implement security, where to place functionalities and all that. Computation and caching, I gave examples there. And so it's a rich field for study. And as we understand these trade-offs and we try to better understand where we're going and how we get there, how to use all these multiple layers at different distances with different capabilities, different mobility patterns, then we may find a rich area for optimization, maybe complex optimization, but maybe with the use of machine learning to search optimal solutions in large spaces, we can find reasonable solutions. And so there's a lot of room for research here. So it's an exciting area to be. And with that, let me stop here because I think my time is up, and I'll be happy to take any questions. Thank you.
Hey, thanks, Michele. It has been a nice presentation and very interesting. So I think that one question there is a question that say that if there were some, you have been more or less asked about possibilities of the losses of high frequency, but what happens when there is a space weather forecasting incorporated? Do you think that the space weather forecasting will be necessary for the non-terrestrial network strategy? Because, for instance, could be, solar storms or something like that, that introduce some type of additional unexpected events in the losses that
yeah, and even rain, right? I mean, there are many things that happen in the sky at different altitudes, which may interfere with the communication. So we do need means to face those events. In some cases with weather forecasts, we can actually predict and maybe plan around these events. In some other cases, they may be unpredicted. And so we must have at the protocol level, means to do error correction or to do rerouting, to have, and if we have a rich architecture in the sky, we may expect to be able to find alternatives or maybe already have pre-computed alternatives to be switched on immediately upon the emergence of any of these events. So definitely is an issue, but the rich infrastructure may actually help facing those types of scenarios there.
Okay, so many thanks. So I think that for time.
Okay, then. Thank you. Thanks a lot, everyone. Let me stop this sharing here and give it back to you. Okay, thanks.
Now is the presentation of the group of the team. I will share the screen. Do you see my screen or not?
Yes.
Yes? Do you see my screen? Okay.
Yes.
So I'm going to maximize. Aquí está. Okay, so I am John Bass from CTDC, and more or less, I am the coordinator of the satellite network roadmap on physical layer of advanced of the eFuture networks. And this group, okay, is currently formed by John Bass from CTDC, Thomas de la Motte from Bundeswehr University, Marcos Giordani from University of Padova, and Ray Sperber is a consultant. Okay, and the outline of today's talk is a short introduction, next generation of waveforms, but the MIMO processing, the optical links over satellite networks, and the millimeter waves for satellite systems, and antennas for 6G and a summary. No, basically that we have been done in these 3 years. No, so as first marketing, no. We are also interested in that the participation of people from you to this group and eFuture networks, no. And if you want to collaborate in the group of the physical layer or the satellite roadmap, then you have to drop an email at me. Here is my address, no. Okay. So basically, I've seen 3 roadmaps. In 2020 we did the first one. That is was in the physical layer, was in waveforms. That was on flexible waveforms, precoding and beamforming, integrated terrestrial satellite networks that we did. In 2021, the second one we did the physical layer was about new MIMO physical layer scheme that was MIMO on radio, on optical wireless, and physical layer for increasing the security, and physical layers for increasing the capacity. So basically, the physical layer not only can be used for providing capacity, can be used for providing other services. For instance, security and robustness also. And 2022, the site roadmap was dedicated to millimeter wave through satellite networks. No, the utility of if possible was be able the use to millimeter wave in millimeter bands. And here we talk the bands of millimeter wave, the missions of the millimeter wave, current missions of satellite missions that are operating, the devices on millimeter waves that is possible to hire or not any device on millimeter wave, and the antennas of millimeter wave. So basically, there are some initial KPIs and on the 6G, that is for comparison, and the evolution of the standards is subject to the value that I think that with the time will appear more accurate values. But the important here, for instance, is the music of the values. No? For instance, you can see that for the peak data rate, you will have an increase of 50% of the 6G compared to 5G. The data rate also the 10. The bandwidth has to be increased a large, okay? The reality has to be very large, okay? And also the mobility. When I saw this table, was for this time, one of the parameters that surprised me was that, because this means that we have to not to think on the extensions in the x-axis. We have to think also in the y-axis, no, in the altitude. So then that means that here is the airplane use case is considered. No, so that means that if you are in an airplane, you have to be connectivity there, and then that means that have to be integration with satellite and an airplane. No, then as a result, in the next generation, satellite will play a key role. No, here you see that with some few data, more or less estimate what technologies more or less will be important. No, and here, as you see, the capacity is a real need for 6G. Then that we do in the group is more or less what to do from the physical layer point of view to increase the capacity, okay? And other aspects are security, robustness to the communications, no? Because it's necessary also a robustness, okay, and reliability. And here from the next generation of waveforms, current 5G, we do analysis. 5G systems trust on OFDM for downlink and single carrier FDM for uplink because it has a lower PIPR. However, of them, I think of firms have a cyclic prefix, okay, that reduce the spectral efficiency, while it's not good for having high data rates, or at least respect to other waveforms. Don't integrate the Doppler delays into the waveforms, no? So then it's difficult, more or less, more difficult to compensate the Doppler, for instance, in mobility scenarios, high mobility scenarios, as will be the 6G, because we have, for instance, airplane in your case. So future waveforms have to consider integrated delays for detections, for instance, orthogonal time frequency for LEO channels or mobility channels, for instance, the airplane, provide a high capacity, perhaps non-orthogonal schemes could be used, okay? Also, non-orthogonal schemes permit to reduce the time or the bandwidth that you are using, and then perhaps provides also a higher capacity, but also robustness or security, because introduce some self-interference with respect to the others, no? So integration as much as possible, optical and radio waveforms. As you see, we need higher capacity, optical bands, and also the radio millimeter waves has a large bandwidth. Then it's necessary, and then more or less to see if possible or not to use as much as possible the relations or that or the waveforms that are used there. Why? Because it's possible that you use not only one medium of transmission, you use multiple of them, and perhaps you will need to use in some part the radio and other to the optical. And in this way, if they use the same waveform as much as possible, then it's lost the performance in the change the medium, and you have to change the waveform is lost. The performance is negligible, and the data rate that you lost also in these changes also is low. And have in optical schemes, for instance, high performance coherence detection schemes that also need, because now are more based in coherence schemes. And here, for instance, from the point of view of MIMO processing, MIMO is used widely in terrestrial networks from Wi-Fi, 4G, 5G. However, in MIMO, in SATCOM, it's slowly advancing because we have a line of sight. So then, in case of MIMO, then, as you know, you use MSA, then there's some instabilities in the MSA. So then that you have to do is more or less study distribution of the antennas of the MIMO system, no? And in this way, for instance, if you use advanced signal processing in order to this study, you can see, for instance, that a different distance, optimum distance for having a gain in MIMO gains in satellite, no? For instance, here for 20 gigahertz, the distance is 96 kilometers, and for 50 gigahertz is 38. This is basically that the higher the variation of the signal, the lower the distance that have to be the variation of the antennas. No, these are results that are provided by the University of Medellín for Thomas de la Motte. Okay, and MIMO processing also will be used in the feeder link. Okay, and in order to reduce the bands Ka, Q, and B, in order to reduce the number of gateways, okay? Because the higher the band that you use, the higher the free band that is possible, then it's possible that reduce the gateways that provide the service of the feeder link. In the multi-user MIMO downlink in the K-band, for instance, you have here full frequency use, and you also can separate the users, okay? And here it's a significant throughput respect to the forward use. And MIMO processing, also the field trial, the Eutelsat 7A and 7B, two geostationaries, provide overlapping downlink coverage, no? And zero forcing precoding used, no? So it's a real scheme that used MIMO processing, okay? And here, in multi-orbit systems in the future, it's expected that distributed architectures of LEO, MEO, megastations to use that. Then introduce of satellite swarms also, and use of seal-free massive MIMO proxies. Where there is interference between different systems, MIMO could be a solution in order to separate the users. And the challenges, the movement of the satellites, the Doppler shift, time-varying churning, that orbital imperfections, and low complexity processing and limited signal overhead. That's especially the satellite. And other part that we have done this year is the viability of optical links in satellite communications. No? Current 5G standard supports free space communications for inter-satellite links. This is acceptable. This is possible. For 6G, new use cases and capacity augments are required. So in this case, it's also for instance that in the future, optical feeder links and access links may be an option for using optical links there, because will be capacity bottlenecks. And then optical or higher bands, as the millimeter bands, radio bands, could be an option for them. No? Not have to be excluded. They can be more or less compatible with them. Hybrid systems. No? That is the idea that I follow always. The hybrid systems. And satellite to ground airplane require to compensate the optical channel and impairments. The optical channel that is impairments as beam boundary and turbulence. No. And for instance, if we see more or less we come from radio, then and we enter in optical, we see that distributions are quite different. For instance, in this case, we see the distribution of the irradiance of the intensity that light intensity that arrive to the receiver for three amplitudes of the telescope. One is of 50 centimeters, one of the green is 10, and the other is 1. The lower this high focus is the telescope, and then we achieve a more or less radio, more or less signal distribution. No? But if we increase the distribution, the aperture, then here we can have another sources of interference that can destroy or reduce the signal to noise ratio of optical, that or signal. No? And here, on the optical wireless scheme, we have some part that is, for instance, the gateway and to the IoT terminal will be one part is optical and can be one part of radio. That's the thinking that they're current. But however, in the future could be this part optical, or radio optical, the same. So that means that in the satellite and the gateways should be more or less and optical links. Okay, the optical payloads. That's the future that we consider. That have to be done. And millimeter waves. Okay, here we have more or less analyzed the available spectrum, and we have that the millimeter waves that has 3 bands: Q, B, and W. The Q is the 40, 42, and 50, and there are 4 GHz available for the uplink and 6 GHz for the downlink. We have 50, 51. We have 1 GHz for the uplink and 4 GHz for the downlink. W, we have 81, 96 for the uplink and 30, 75, 76 for the downlink. No, and we have 5 gigas and 1 gigas. No, you say more or less here the viability, for instance, for the feeder link, the satellite. We have, for instance, for the uplink will be more or less in the Q band, and the downlink you can do and I guess here the millimeter waves propagation. Here we see that the path laws that Michele has previously commented, the basic path laws, the entry path laws, the tropospheric oscillation, atmospheric observations, and results are provided I have to say that by the University of Padua, contributed by Marco Giordani. Okay, and here, as this is not necessary to repeat, that is the same changes as channel modeling, spectrum, physical layer procedures, all of them have to be and solutions that can be more easily configurable. The layer solutions have amplitudes that provide And the meter waves, some results here. You can provide high emitters. You have here LEO satellites at 6, 20, 70, and 150 gigahertz for dense and rural. Of course, you see that for dense, well, you have a lower capacity, and for the lower elevation angles, you have a lower capacity. Okay, that's because you have a higher blockage probability. However, you have, if you use hubs, you increase the capacity. Then especially for the low elevation angles, no, and then you increase the capacity in all your cases. So regarding to antennas, the antennas, there are 3 parts: for capacity, robustness, and security. High communication capacities, the antenna system is really interoperable, and security system elements must not interfere communication security, no. And the antennas for 6G, there are 6. They are according to the link, the ground stations now are in the large C, X, and Q band, but in the future expected to use Q, B, and W bands. The same for the feeder links and the user links, okay? And the intercepted links, also smart reflector antennas in telescopes, and end users multiband. Here, this part has been provided by RAI, okay? RAI Sperber. And the summary, here we see a physical layer. Next to my side, the interface and the capacity. And here, MIMO, millimeter wave, and optical wire links could be solutions. The waveforms, flexible, low PRPRN support, LEO scenarios, it's suitable. MIMO techniques, exploitation of precoding techniques to remove possible interference, integrate optical links in feeder links and access links, that's a solution. And millimeter wave can provide increasing the capacity in urban scenarios to use with hubs, also increase the capacity during catch. Also, simulators that integrate multiple radios over satellite, it's a real need in this part. And also, for satellite antenna systems, possible solutions, basically reconfigurable multiple feed antennas, no, with electronic PMS steering. So, from my side, that there is nothing more to say. If questions? Okay, so I think that there is no question here.
John?
Yes, you have any questions?
I have single.
Increasing the frequency, we have to sometimes ask if they are energy efficient, because photonics is more energy efficient than electronics, no? And then I don't know if it compensate, increase the bandwidth, no? And then it's better to use in radio and use other bands as optical, no? For instance, it's my impression, no?
Okay, thank you.
I'd like to make an observation here. This is Ray.
Okay, Ray.
When an operator is using these, he's not constrained to stay on one line. And there's actually quite a bit of creativity that's possible. And I know of satellite operators that are implementing this. For instance, you don't use, it's, as you get the 70 gigahertz band is going to be very challenged with propagation. But
Ray, it's challenging at the beginning, but with the time, and then we start to learn how to manage that, and then we find solutions. It's always that happens.
Yes, of course, but
otherwise there will be research programs.
I mean, unless you want to make all the surfaces adaptive, or an array with all the elements adaptive, I think it's going to be hard. But the point is that one can, for instance, look at the Q and V bands. Basically, they overlap, don't they? If you can make your channel from say 47.2 to 51.4 and just not use the or use somehow work a way to work the gap between the 50.2 and 50.4.
Yeah, I agree with you. I agree with you.
Yeah.
It's
And that is commonly done.
Yeah, I agree with you. It's in
Right,
fact
that's all I wanted to say about that.
the distribution of the bands, or the frequency bands, for instance, in the Q band is crazy sometimes. Yes, I agree with you. So from my side, I have finished, and then comes the last paper from Malek. Malek, are you here?
Yes, I'm here.
Okay, so then you can start.
Okay. Can you see my screen?
Yes.
Okay. So, hello and welcome everyone to this presentation. Thank you very much for giving me the opportunity to be a part of this workshop, and a big thank you for the organizing committee. So today I will be presenting an overview of precoding techniques for high throughput satellite communication systems. And this summarizes our survey of the literature of precoding for high throughput satellite communication systems, which is a work in collaboration with Dr. Abla Kamoun and Professor Mohamed Slim Alwini. Okay. So the outline of the presentation will be as follows. We will start by the motivation behind the survey. Then we will give a quick background of the basic concepts of a satellite communication system. Then we will present a classification of the precoding techniques for high throughput satellite communication systems. We will discuss some of the practical system impairments and present some robust precoding techniques. Then we will present some future research directions before we conclude. So the motivation is mainly the fact that now high throughput satellite communication systems are emerging as a key technology for the future communication generations. And when we say high throughput satellite communication systems, we are talking about an aggressive frequency reuse across multiple narrow beams instead of a single beam. And since we have multiple beams, we have an increased rate at the expense of a higher interference. And in this context, precoding emerges as a prolific technique to enable this aggressive frequency reuse. So a typical satellite communication system will have a ground segment which contains the gateway and the control facilities. We will have a space segment that will have the satellite constellation and user segments that will be deployed on either fixed or mobile platforms. And this, like all of these components, will be sending and receiving signals within a certain allocated frequency ranges. And this is a summary of the main frequency ranges and their applications. So since we're talking about precoding, one relevant modeling aspect is the channel, because precoding is, we will utilize what we know about the channel or the data information to mitigate interference. So the basic two models that are used are fixed satellite communication, fixed satellite channel models, and mobile satellite channel models. Fixed satellite channel models are models that are above 10 gigahertz. They're characterized by a line of sight. However, they suffer from significant tropospheric phenomena. On the other hand, mobile satellites are below 10 gigahertz. They are characterized by a line of sight and a non-line of sight component. However, tropospheric phenomena become irrelevant in this context. Now, moving on to a classification of the precoding techniques for satellites. So this classification is done from two main perspectives. The first perspective is a problem formulation perspective, and the second is from a system design perspective. From a problem formulation perspective, the precoding techniques for satellites can be classified or categorized according to first the precoding group, which is the scheduling strategy that is incorporated in the precoding design. And it can be either unicasting or multicasting. The precoding objective, which is the optimized objective function that the precoding scheme is designed to optimize, and that involves spectral efficiency, energy efficiency, secrecy, or even mixed objectives. And the third classification is according to the precoding level, and we can have block level precoding or symbol level precoding. Now, from a system design point of view, precoding can be classified or can be categorized according to first the system configuration. That means, are we considering a single gateway or multiple gateways? The second is the precoding implementation, whether it's implemented on board, on ground at the gateway, or in a hybrid fashion on board and on ground the gateway. And the third is according to the satellite service, whether we're considering fixed or mobile satellite services. So starting with the precoding group. So in a unicast scenario, which is in the literature, there has been a lot of work that consider the unicast scenario to design the precoding scheme. Generally, in one time slot, only one user per beam is scheduled, and the precoding matrix or precoding design is optimized to minimize the interference between each of these scheduled users per beam. So the second is precoding group, which is the second scenario is the multicast scenario, which is the practical scenario, which consists of scheduling more than one user per time slot. So in each beam, we will have more than one user scheduled, and then the precoding will be designed to mitigate interference between the users across all the beams. Now, if we compare these two scenarios that are treated in the literature, the first is not practical for real systems. However, it can give insight, and its design is more, it's easier because we only consider the demand satisfaction and the interference mitigation. On the other hand, multicast is more compatible with the satellite communication standards, and it's definitely more practical. However, it has more additional design constraints because the multiple users that will be scheduled within the same beam will be served by the same physical frame, and therefore they have to have similar channel conditions for the precoding to be really performant. Now, moving on to the second precoding to the precoding category, which is the precoding objective. So there are multiple objectives that are addressed in the literature, and here we can categorize them in three main categories. The first is spectral efficiency, which involves the classical problems of sum rate maximization, max-min fair problem. The second is the energy efficiency and power efficiency, and this is a really important problem for satellites because these are really limited resources for satellites. So objective functions in this context can be the sum power minimization or energy efficiency maximization. There are also secrecy metrics that can include secrecy capacity or secrecy rate that also can be optimized using precoding. And the fourth category is mixed objective. And in this category, the precoding weights are not the objective function is not only optimized for the precoding weights, but also is optimized for other parameters such as scheduling or power allocation or carrier allocation. don't know, I think there is a delay because I can't change the slide. Okay, now moving on to the third classification, which is according to the pre-coding level. And there are two levels where we can do pre-coding. There's block level pre-coding and symbol level pre-coding. Block level pre-coding mainly differs from symbol level pre-coding by the fact that in block level pre-coding, we aim at eliminating interference completely. So here we have a target signal and the pre-coding weights are optimized to cancel out the interfering signals. However, for symbol level pre-coding, we have a target signal, but the interfering signals are rotated in a way that corrects the detection region of the target signal. Now, these two can you see my slides moving or?
It's your 15th slide now.
Because it's not changing for me. I think there is a delay. Just 1 second.
Okay, 18, 16.
Okay, so if we compare block level pre-coding to symbol level pre-coding, block level pre-coding relies only on the CSI, and therefore it's optimized over a block of symbols and is characterized by a lower switching rate and therefore lower computational cost, which is important in the context of satellite systems. However, symbol level pre-coding relies on both the CSI and the data information of the symbols, and therefore it's optimized for each of the symbols, and it can outperform block level pre-coding at a higher switching rate and a higher computational cost. Now, from a system design perspective, pre-coding can be categorized according to the system configuration, which it can be either a single gateway or a multiple gateway. Multiple gateway systems are basically different from a single gateway system in the fact that the beams are not fed by the same gateway, but fed by different gateways. And this can be formulated such that the coding matrix of the whole system is a block diagonal matrix where each block corresponds to a gateway. Now, if we compare these two configurations, single gateway systems have a very high feeder link requirement that can be practical for real systems. However, it has more degrees of freedom to design the pre-coding scheme because the single gateway will have access to all the feed signals to design the scheme. However, and also it has the advantage of no signaling overhead. On the other hand, multiple gateway systems they have less feeder link bandwidth requirement at each gateway. They have a less computational cost at each gateway as well. They also are more robust against gate fails. However, each gateway would have less degrees of freedom to design the pre-coding scheme because it will only have a part of the feed signals. And there will be also a high signaling overhead because the gateways will have to communicate between each other and exchange CSI in order for each of them to design its pre-coding matrix. Moving on to the pre-coding implementation. The implementation of pre-coding can be either on board or on ground at the gateway. The onboard implementation usually is analog due to the limited variability and power resources on board the satellite. It's also generally user agnostic because it does not use instantaneous CSI of the users, but rather it has more, it's designed according to the traffic and to the general propagation conditions, and therefore it has a quasi-static nature. And it has the advantage of a lower feeder link bandwidth requirement compared to on-ground implementations, because on-ground implementations are usually like we use baseband digital processing to implement them. They're user aware because they use the instantaneous CSI of the users. However, they have a higher feeder link bandwidth requirement. A trade-off between these two implementations will be a hybrid implementation on board and on ground, which consists of decomposing the precoding matrix as a product of two matrices, which one will be applied at the gateway and the other one will be applied on board using analog components and phase shifters. This gives it lowers the feeder link requirement, but also it lowers the performance due to the analog processing on board and also the limited degrees of freedom. Now, considering the satellite service, the precoding can be also done for fixed satellite services, and recently precoding has been investigated for also mobile satellite services. Fixed satellite services, they transmit to fixed Earth stations. They're typically in the Ku and Ka band, and they have higher path loss and rain fading. And they also require larger and more expensive antennas, offering more focused beams. On the other hand, mobile satellite services, they transmit to mobile terminals. They're typically in the L and S bands. They have a lower path loss and rain fading. However, they have a cheaper antennas. And the literature of precoding has been focusing more on the fixed satellite services. However, there have been recent attention towards applying precoding for mobile satellite services. When we compare mobile satellite services and fixed satellite services, mobile satellite services have to deal with the user mobility and its impact on the CSI. And there has been works in the literature that show that the impact of user mobility on the CSI can be limited considering robust CSI feedback mechanisms. Now, most of the literature in precoding hypothesizes perfect transmission conditions and perfect channel conditions. However, in practice, satellite systems are subject to multiple practical impairments, and these impairments can be transceiver and payload impairments or channel impairments. The transceiver and payload impairments are nonlinearities coming from high power amplifiers and phase perturbations coming from oscillators, instabilities, and Doppler effects. The channel impairments, they come from the CSI estimation errors and also the delayed CSI errors. And there has been several works addressing these problems and proposing more robust precoding techniques. There has been works addressing more robust precoding techniques against phase noise, and it pretty much consists of modeling the phase noise as a random variable and adding it to the estimated channel. And this makes the SNR a random variable, and the precoding problem becomes a stochastic. It will have a stochastic nature, and we will have an outage maximization, for example, or an average SNR maximization. designs accounting for non-linearity of high power amplifiers. Generally, these nonlinearities can be modeled. There are various models in the literature. One common model is Volterra series, and for robust precoding technique against these nonlinearities, there are mainly two approaches. The first one is to limit the maximum signal amplitude to ensure that the high power amplifier can operate in a linear regime. And the second is to solve the precoding problem in the general framework of nonlinear signal pre-distortion. Now, for future topics, for precoding for satellite communications, there is first the flexible precoding, because flexibility is now we want more flexibility in payload, we want more flexibility in resource management. So there has been generally flexibility is implemented via flexible allocation of bandwidth or flexibility in time using beam hopping. However, there has been an attempt or a study to combine both precoding and beam hopping to come up with a flexible precoding. And another future topic is the onboard processing and the hybrid precoding that involves both analog and digital domains. And finally, precoding for mobile satellite services is another potential future topic.
Okay.
Thank you very much. I will be happy to answer any questions.
Okay. Yes, there is a question that the precoding that you are considering is applied to the uplink or the downlink?
The downlink.
Downlink. Okay.
Yes.
Any reason in particular?
Huh?
Any reason? Any reason? You can extend the answer.
Excuse me, any reason to extend the network?
No. Why do you think that you are considering precoding for the downlink?
Yeah, so for this context of full frequency reuse, and we have like we are applying multi-user MIMO techniques, right? So for the downlink, generally the interference mitigation is performed by applying precoding. However, when we are talking about the uplink is generally addressed with multi-user detection.
Okay, perfect. That's all. Okay, so I think that the physical layer session has finished. Okay, so then we have to start it with a roundtable, but it seems that we are late. And then the roundtable, it seems that organizers say that will not possible. But in any case, I would like to thank to all presenters the presentations because they are of very high quality, and also especially also the team that I collaborated with, that is Ray, Marco, Thomas, all the members, no, and Giovanni also during these days. Okay, so many things. I think that Giovanni, I think that the floor is yours because I think that this session is yours now.
No. Next session is handled by Zili soon.
Okay.
I think we have a 5-minute breaks if you like, Zili, and then we can start.
Okay.
Yeah. Okay. I think we have a 5 minutes break. Everybody can have a cup of tea, and I will load up my schedule to start. You know, we have four. Okay, we have a break now.
Recording stopped. Recording in progress.
Okay, good afternoon. Sorry, it's on mute. Okay. Oh, hello. Sorry, I just forgot to unmute myself. Good afternoon, good evening, good morning. Depending on where are you. And in this session, we are the first session of the quality of service. This is related to the quality of service, quality of experience, and key performance indicator for 6G satellite network. In this session, we have 4 presentations. The first one will come from China, Dr. Shirley Kang. The time over there was early morning, 3 o'clock. That's very challenging. The second one will come from Germany. This the Central European time. The third one is a joint paper between the Ireland and Saudi Arabia. So that's also very challenging. It's an interesting paper. And finally, myself and Giovanni will share the paper and give it a presentation to look into the work we've been doing related to the QS, the satellite networking roadmap. After this, I think we will have a round table with the speaker. Just quickly remind everyone, for tomorrow, the starting time will be earlier than today. And that will be 7 o'clock in East daytime. That's, I think, European time. That will be the 1 o'clock in the afternoon, Central European time. Can you please check the website to make sure you get the right time and welcome to join tomorrow's session. Without further discussion, I would like to invite our first speaker, Dr. Shirley Kang, to give a talk. Hello, Shirley?
Yes.
Okay, can you share your slides? Stop sharing.
Okay.
Okay, thank you.
So, can you see my screen?
Yes, we can see it clearly.
Okay, I can use the full screen. So, you can see the full screen?
Yes, full screen, okay. Yes.
Okay, it's rather early morning in the east, and also it's in the afternoon or in the evening for the west. So say hello to everyone, and good morning and good afternoon and good evening to everyone. I'm Song Li. My topic is the trends, challenges, and the key technologies of integrated terrestrial satellite communication. In fact, from the above session, I found this topic is rather similar to that from Professor Michael. So maybe you will feel more familiar with the content of my presentation. So this is the abstract. You can see if on the website, I just skip it. I have 3 parts for this presentation. The first, I will introduce the background and the developing roots of ITSC. So for me, I have been I have been doing research on terrestrial communication from around the year 2000. So it's nearly it's more than 20 years. But around 2016, I began to do the research about satellite communication. So from doing the work, I'm thinking how to do the work for satellite communication. We know for the terrestrial communication, we have upgraded from 1G to present 6G. So we have great dreams for terrestrial communication. We have many visions. But at present, current terrestrial communication only serves less than 10% of the global area. So the served population is around 70%. So that means for the terrestrial communication, so we have the dream, it serves everywhere, but it really serves only in limited area. Compared with the terrestrial communication, satellite communication has the advantages of wide area coverage and also seamless coverage. Especially in recent years, the satellite communication has its climatic period for its development. From the present development for satellite communication, we found some phenomena. For example, traditional satellite communication only provides narrowband voice, but present satellite communication can provide broadband data, and also the constellation is changing greatly. For traditional satellite communication, we only have several. Usually we see less than 100 satellites, but at present we have thousands of satellites for a constellation. And also traditional only have transparent satellites, but now we have regenerated satellites, and also we have the inter-satellite link. So there's a lot of changes for satellite communication. Here we show a table about the recent satellite communication for LEO. From this table, we can see OneWeb and Starlink is developing very fast. They are in commercial. So the satellite communication is developing very fast, but we see it's a standard. We found the standard is usually is rather late compared with the terrestrial communication standard. Sometimes it refers to the terrestrial communication. Here we show some tables for traditional satellite systems. We can see they use similar standard as the terrestrial systems. This means we need to do some work for the standard for the satellite communication standard. Fortunately, we know some international organizations are doing this work. For example, 3GPP and ITU have done more work about the satellite communication standard. For example, non-terrestrial communication, non-terrestrial network. This NTN has been studied in 3GPP since year 2016. But from the and also because NTN is research since 5G, but from the industry and also academics, we know more and more researchers are thinking how to integrate satellite and terrestrial toward 6G. So we are thinking, what's the relation for satellite communication and terrestrial communication? And from our reports, we think the ITSC should have two stages. The first stage is in 5G. This satellite communication and terrestrial communication, they are compatible. That means satellite communication can be compatible with terrestrial 5G communication by maximally using 5G technologies. The second stage is for 6G. We think the satellite communication and terrestrial communication, they are fully integrated into one single system. We will give more detailed information or explanation about these two stages. So here we show some. We just give simple figures to show these two stages, to explain these stages. After explaining the background and developing roots of ITSC, we want to analyze the challenges and the key technologies of ITSC in 5G and 6G. First, let's see the challenges and the key technologies in 5G. I think everyone may be very familiar with these key factors. Here we show the difference between the satellite link and the terrestrial link. For example, the channel propagation is rather different because for satellite link, we have large distance, and that means large delay. And also for LEO and MEO, we can see the satellite is moving around the Earth. So we should consider some problems of synchronization, and also we should consider some technologies for handover and also for uplink accessing. And also the satellite mobility will also have some effect to the modulation and the coding and more. So and also we should consider the satellite mobility on paging. So from this difference, we think in our research for the satellite communication relating, if they using the terrestrial communication standard, the satellite communication should consider should do a lot of peculiar particular research, we think we have at least include 4 aspects. First, we should consider some basic issues like channel modeling, link, and also we should consider some evaluation method that will be different from the terrestrial communication. And also, we should consider link budget and also frequency reuse and more. Also, from the second is about the network architecture. We know for depending on the capability of a satellite, we may have the band pipe type, or we may have the regenerator type. So they will have different architecture. This is also the work that we should do. And also, we in our system design, we should consider the some key aspects on physical layer and also high layer. For example, from the physical layer, we should consider the waveform, modulation, coding, beamforming, and also the communication process. And also from the high layer, we should consider paging, mobility management, routing, and more. Here, we give two tables to show the satellite standard relating to the terrestrial standard. Is comparison with the traditional satellite standard DVB S2X. From the research, we think 5G-based satellite standard has some advantages compared with the DVB S2X because the 5G-based satellite standard, they not only have the physical layer, but also have the higher layer and also the whole network. And also they can support some key technologies like the synchronization, HAC, control channel, DRX, RM, measurement, and also mobility management and more. So based on this analysis, we can see that the 5G-based satellite communication really work. We should also overcome a lot of challenges, including the propagation channel and the mobility of the satellite, and also we should consider the transmission distance from the communication link, and also the beam type of the satellite, because usually satellite uses directional beams, wherefore terrestrial communications sometimes or usually we use the omnidirectional beams. And also for the cell radius, we should consider, because for a satellite beam, it covers a large area, where in this large area, we should consider more user end or more terminals. So the density is or the number should be much bigger than the terrestrial communication, than that in the terrestrial communication. Here we shows the key technologies that we should consider for 5G-based satellite communication. From the table, we can say we should consider the duplex mode, the waveform, because for satellite communication, we usually say we need low PAPR. And also we should consider coding and modulation. And also we should consider the Doppler frequency shift compensation, because for layer, the satellite moves fast and it brings much higher Doppler shift than in terrestrial communication. And also we should consider the timing and also the access, and also the MIMO. Actually, it's not a massive MIMO, but it's just a virtual MIMO. I will give more detailed information about the virtual MIMO in following slides. And also, NOMA also can be considered for satellite communication. In the above session, some speakers also has discussed this technology. And also we should consider the mobility management and also paging. And also paging is rather different for 5G-based satellite communication compared with the terrestrial 5G. Okay, finally, we will show the challenges and key technologies of integrated terrestrial and satellite communication towards 6G. From this figure, we can see in our imagine, we think in 6G, the satellite and the terrestrial can be integrated from a lot of aspects, including the terminal, the frequency, the resource management, the platform, the network architecture, and also the area interface. I will give more detailed information in following slides about these kinds of integration. Here we show some challenges for the integration work in 6G. We think it includes at least 3 aspects. First is the multi-layer network correlation and management. Second is the limited load capability of satellite. And the third one is the dynamic routing among the inter-satellite links. Also here, we show more detailed texts, but because the time limited, I didn't give detail introduce. And we have listed some key technologies to overcome above challenges. First one is about network architecture. Here, we show a general architecture for the integrated satellite terrestrial system in 6G. From our viewpoint, we think each satellite is just an accessing node. And also the terrestrial base station is also an accessing node. For the core network, it will manage all the accessing nodes. With this general architecture here, we show more detailed information to how to use the architecture or how to control and manage the capability of each satellite. We can design the flexible architecture for each satellite. For example, if a satellite, for example, the GEO, it can have the high payload, so we can take more functions on it, including not only the general base station, but also some part of the central network. But for layer, usually we can only, its payload can only be composed of composed of a general GNB or just the distributed unit or centralized unit. And for the ground or for the central network, we will have 4 functions, and also we need to do the management and control for above all loads. Also from the air interface, we wish to build a unified air interface for satellite and terrestrial. And here we show some examples about some key factors for the air interface design with the different parameters for terrestrial and satellite. But they use the same mode but different parameters. And here we choose the concept of virtual MIMO to be used in satellite communication. Because for terrestrial communication, MIMO is the best efficient way to improve the spectral efficiency. So for satellite communication, we usually use seesaw, but we can combine or we can coordinate multiple beams to compose the virtual MIMO. By this way, we can improve the spectral efficiency for satellite communication. And for the beams, for the correlated beams, we can use the beams from a single satellite or beams from different satellites, or even the beams from satellite and also terrestrial base stations. And also for we think multiple access and even normal is a key technology to be used for the IPSC in 6G, especially for the satellite communication, since the coverage area of each beam is rather big or is very large. So NOMA is more necessary in satellite communication than in terrestrial communication.
Maybe you can speed up a little bit. The time is over. Yeah.
Okay. Okay, here we also show the beam hopping and the beam switching. We can, in satellite communication, we can use we can separate the control beam and also the service beam. For the control beam is just used for the signaling transmission, and the service beam is for the data transmission. Here we show some research results, and it's also can be seen from our published paper. And finally, we can. Not finally, we can also have key technologies about the load balancing routing. This is the last one. We can consider the spectrum sharing and also related interference management for the satellite communication and the terrestrial communication. If they use the same spectrum, we should do the interference communication, interference management, and also we should consider different frequency. We should have different policies with different frequency band. Okay, just give a very simple conclusion. I think satellite communication and terrestrial communication are both developing rapidly, and the integrated terrestrial satellite communication will take advantages of their both separate systems. And in 6G, we think we can imagine there will be integrated systems for satellite and terrestrial communication, and we wish to synthesize unified network. Here also shows some published papers to support this presentation. Thank you. That's all my presentation.
Right. Thank you very much, Dr. Kang. And I think we can have one question if anyone have any question. I have a question here. So excellent study. Please refer to paper here for us to follow up. Okay, I think we can let you have the paper to follow up. One of the question from me, you know, you have the link between the Geo and Leo. You know, what kind of link you consider in that network design?
We think for Geo is the research the theory is very simple. So in our research, we consider layer at the moment. Because it's more complex, we should consider more technologies. These technologies is resulted due to the mobility of layer. But for the Geo, since the satellite is almost static around the Earth, we think it's very similar as that in the terrestrial communication. So we need a lot to do more work. It's very simple. So we didn't consider this case. We just consider a complex case. Thank you.
Thank you very much. I think thank you again. And the next the speaker will be I think Flora Volker is there from Germany. The title of the talk is the performance evaluation of 5G backhaul via Starlink. It's an interesting topic. Could I invite Flora? Are you there?
Yes, hello.
Hello. Thanks for joining us. At,
good evening, good morning.
Good morning.
Good afternoon.
I think good evening for UK.
Yes.
Yeah. I'll let you to share your slides, and then you can start your talk when you're ready.
Okay, perfect. No, I hope now this is the wrong mode. Just wait a second.
So you can in the middle. Okay, I think I can see you now.
Just one moment. It seems the wrong screen.
Okay, because I couldn't recognize your menu. You try to share your screen. Okay, it's coming. Yes.
So I hope now you can see it.
Yes, perfect. Thank you very much. Can you limit your presentation 25 minutes to give us some time for question?
Yes.
Thank you very much.
Okay.
Thank you.
Hello, everyone. So the talk will cover the topic performance evaluation of 5G backhauling via Starlink. So I would just like to introduce our entity, the University of the Bundeswehr here in Munich. Basically, we are here at a university in Germany, and we covering mainly all the relevant fields, starting from fundamental research, applied research, but also field trials and over-the-air tests. So this talk today will rather cover a more applied research topic, where we did some over-the-air tests with a commercial off-the-shelf Starlink terminal. So as you may all aware of, usually in the 3GPP cellular networks, we have the radio access network on the left side where you have the base stations, and they're usually connected via the transport network, which is either fiber, RF link, and in some cases GEO satellites to provide the backhaul towards the core network. Nowadays, with the new mega constellation, it seems to be feasible to also use low-flying satellites for the transport network. And that was the application or the use case we wanted to investigate in the study. And therefore, we provided a testbed, or we set it up a simple testbed, which allow us to evaluate certain protocols via the Starlink-enabled 5G network. Basically, our architecture is very simple. It consists of 3 computers. One laptop is connected to a 5G router. The UE provides the link via the radio access network to the GNODE-B. So we use a software-defined GNODE-B solution from a French startup company called Amarisoft, where we provide a 40 megahertz single input, single output radio access carrier. And this base station is basically backhauled via the commercial off-the-shelf closed Starlink solution. And of course, we don't have access to the Starlink teleport. Therefore, we need to close the additional link via the internet towards our third computer, where we have the core network to do the end-to-end evaluation of this architecture. However, there are certain important steps which needs to be considered to do such a test, because at the end, the question is, how can you really connect the base station with the core network? So there are several things which needs to be considered. However, to evaluate the basic performance of our base station, of course, we did some evaluation in the lab, just using a local area network and a VPN client, in this case WireGuard, which seems to be the best VPN solution in that case, where we just evaluated the baseline performance of the whole 5G end-to-end network. And the performance is really close to the, let's say, the information you get from the 3GPP document when you assume a 40 megahertz carrier with a single input, single output system, and adaptive modulation encoding up to 256 QAM. So in this case, for the most prominent transport protocols, UDP and TCP, you achieve, let's say, up to 26 megabit in the uplink of the 5G cell, and around 140 mbits in the downlink. So this is basically our baseline. So this is what our 5G cell can provide. And now the first important question we had was, okay, how can we close the backhaul link? Because we don't have a direct access to the Starlink teleport. So our first idea was to use the SCTP protocol, which is basically the main control plane protocol for the connection between the GNODE-B and the core network, and we wanted to do this via the internet. However, as some of you may aware of, this protocol is very sensitive to NATs, and therefore, it seems not to be feasible to use it directly via the Starlink network. We also tried it via some mobile networks, and it was the same. So it seems that these networks don't support it, and we can't really close the link. So therefore, we evaluated 2 VPN solutions. First, OpenVPN, and second, WireGuard. However, it seems that WireGuard, for this purpose, fits a little bit more. So we had, let's say, around 5% throughput loss compared to the poor Starlink internet service. With OpenVPN, it was more significant, let's say up to 30%. And therefore, we selected the VPN application WireGuard to conduct our measurements. Basically, we wanted to compare two services in the first step. So the Starlink baseline architecture, where we have no 5G network involved. We just have two computers. They are connected via the Starlink network and the internet due to the VPN link, and we evaluate basic transport protocols such as TCP, UDP, and also the new protocol QUIC. And we also did the same for the Starlink 5G backhaul, where we now also have the radio access network on the left, or on the bottom left side, and the core network on the bottom right side. This slide now covers the measurements we did for the transport protocols. As I said before, we did it for 3 types: TCP, UDP, and QUIC. However, for TCP, we did 2 kinds of measurements. So the first one was just a single TCP IPERF stream, and the second one was 10 streams in parallel. And yeah, what you now can see that, of course, these transport protocol do really are really affected when you have some packet loss. So you really can observe with TCP some losses, because there is no performance enhanced proxy which can be used, or which might be there when you use the pure Starlink service, because the whole traffic is encapsulated within the VPN tunnel. So therefore, we observed what we expected, that the TCP performance decreased compared to the UDP performance. And what you might also notice that in our case, the 5G uplink quality was a little bit reduced. When you remember the previous slide, we had up to 25 megabits in the uplink. However, the Starlink network itself seems to be the bottleneck in that case. So with the Starlink VPN, with the pure Starlink service in the uplink, we achieved data rates up to 15 megabits per second. And this is basically the bottleneck in our case. And the 5G network itself can't really upload more data, because the Starlink satellite constellation doesn't allow this. However, for the downlink, it's vice versa. So as you see in the bottom left picture, the Starlink downlink allows us, let's say, a median TCP throughput of around 180 megabit per second, where we just reach around 140 megabits per second when we use our 5G cell. So as I said before, this is just a single input, single output cell with a 40 megahertz carrier. When you use maybe MIMO technology, this could be increased. However, this was what we observed during the transport protocol evaluation. The next slide just summarized the results. What I showed basically in the previous slide. You can observe that the Starlink uplink performance, let's say for TCP, is around 11 megabit per second, and you achieve nearly the same performance for the 5G Starlink backhaul for UDP. And for TCP, when you have 10 TCP streams, it was a little bit better. However, when we have the Starlink backhaul, this was decreased. On the other hand, on the left table, we see the Starlink we see the Starlink downlink. And as I said before, with the poor Starlink baseline in, let's say, UDP, we achieve up to 175 megabit per second. And with the Starlink backhaul, it was reduced due to the capabilities of the radio access network. So as a conclusion of our transport evaluation, so currently, at least for our case, it seems that Starlink is the bottleneck in the UE uplink. So let's say even when you use MIMO technology, your cell can't use a larger uplink traffic due to this limitation. For the Amarisoft radio access network, it seems to be the opposite thing. So the downlink was limited due to the constraint we had with the single input, single output system. And of course, the packet loss of the satellite system affect connection-oriented protocols such as TCP and QUIC much more compared to UDP. So this is also maybe the case because no performance-enhanced proxies can be used because we use a VPN link between the GNODE and the core network. So on the other hand, we also did some round-trip measurements where we basically just want to highlight that with the Starlink-enabled 5G backhaul, you are able to achieve latencies below 100 milliseconds, which is significant when you have a look at geosystems. So usually you are in the range of 500 milliseconds, and this significantly affects certain protocols. And I now want to have a look at some application in the next slides. So our first application-related measurement was related to web browsing, and therefore we used a few browser APIs. We used the open source tool chain called BrowserTime, where we identified two KPI metrics. It was the first contentful pane. So this metric measures the time from the navigation where the browser renders the first bit of the content. And the second metric is the page load time. And so this is the time it takes to load the page from the initiation of the page to load the page completely in the browser. And we did this measurement for 28 websites out of Amazon's Alexa's top 50 list. And all these websites were loaded 10 times. So first, without cache content. So we really loaded the website for the first time. And then the second measurement was with cache content, where the browser already has some information and some figures stored in the cache. Of course, what we see in both figures, with the cache content and with the no cache content, for this website, as we have kind of a double internet hop. So first we have the internet hop, which is used for backhauling to our site here in Munich, and then the 5G traffic terminates here in our core network. However, we still need to reach the website, which is in the internet, and therefore we have a next hop from our location towards, let's say, the next internet gateway. And basically this is what you also can observe here in the measurement. So when we have a look at the top left figure, at the two measurements on the right side, where we have the Starlink baseline website web browsing measurement, basically the backhaul measurement time is twice as much. So this basically, due to this additional internet hop, we have to consider in our architecture. With the cache content, however, the times to load websites reduces significantly. However, we can't really avoid this double hop, and yeah, you clearly can observe it. The next measurement we did was related to voice over IP. Therefore, we used the SIP-based voice over IP toolchain. It's called SIP with double P at the end, and Wireshark, where we transmitted an audio file. And this audio file was transmitted then via RDP, of course, with an average data rate of 64 kilobits per second per call. And we did multiple SIP calls in parallel. So what we observed were jitter drops where all the voice streams were affected at the same time. So let's say when we had 70 VoIP streams in parallel, all these VoIP streams were really affected at the same time, as you can see here in the right picture. And it seems that due to the satellite handover of the satellite constellation, you have some jitter drops or performance drop where you have some packet loss for a few milliseconds due to the satellite handover, or at least this is what we assume, because all the packets are affected at the same time. And this is really a pattern which regularly occurs. What we observed for the 5G uplink, we are able to do up to 70 VoIP streams in parallel, where let's say 100 of 100 were successful, even with an acceptable quality. And for the quality measurement, we used the mean opinion score as a metric and the Google Viscol toolchain. And this allows us basically to evaluate when the performance of our voice over IP calls decreases. Let's say 5 is a very good value, a very good mean opinion score, when we only have around 20 or 30 calls. But when we increase the number of calls in parallel, this metric significantly decreases. And usually, let's say below 4, you can't say that it's a good voice call anymore or a very good voice call anymore. So yeah, you already also can really listen that the voice quality decreases. So basically this covers what you can expect when you use the 5G uplink and the Starlink enabled backhaul to do voice over IP. The next measurement was related to a 15-minute YouTube live streaming. However, in that case, we only had a single user and let's say both the Starlink baseline measurement without any 5G involved and the 5G backhauling. The metrics were quite similar. However, with the 5G link in between, we observed some additional dropped frames, and we assume yeah, this is due to the radio access network, where you also have an additional air interface in between, where some packet loss can happen. As you clearly can observe, we easily are able to achieve or to use full HD quality, both via the Starlink baseline connection and also via the Starlink backhaul. However, we now have also some recommendation for future developments. So as we really observed for the web browsing, this double hop could be a problem for any let's say internet related application, and therefore it could be better if we just use the WireGuard VPN tunnel towards the core network for the control plane communication. And an idea could be to have an additional user plane function of the 5G core network, which is then located at the Starlink user terminal antenna. And this would allow us to directly use the Starlink internet service for any internet-related application, without going over the VPN via Starlink to the core network and then to the internet again. So the conclusion of this talk is Starlink and 5G small cell and a VPN tunnel basically allows you to do rapid deployment of 5G cell utilizing commercial off-the-shelf Starlink terminals. So this is kind of a private network which you can deploy anywhere where you have the right to use the spectrum. However, what we really observed that only a few user terminals are currently able to support these private networks due to the limited PLMN IDs. However, currently 3GPP is working on it under the terms of non-public network, and hopefully in the future more UEs can support such private networks. What we observed is we don't see any subjective performance limitation for a single user compared to the poor Starlink internet when we have a 5G backhaul involved. One really limitation you need to consider is that the Starlink uplink limits the performance of the 5G uplink performance, and the additional internet link or the additional internet hop needs to be considered for any internet application, and therefore this user plane function deployed at the Starlink terminal site could really improve future deployments of such an architecture. Last but not least, you really need to consider that real-time applications such as voice or video calls could be affected if the Starlink antenna switches to another satellite. So we observed packet loss, let's say every few minutes, and therefore this real-time application are affected. And you need to consider it when you want to use it. Okay. Yes, thank you. Basically, this covers our experiments we recently did with a private 5G network and the closed Starlink constellation. And yeah, hopefully this was useful for you. And I would be happy to answer any questions you have now.
Oh, great. Thanks very much to keep the time. Thanks, Florian, for the excellent presentation. And is there any question? I haven't seen any question. I think I have a question for you, Flora. Hopefully it will be not too difficult for you. One of the questions is, the Starlink, you can directly use access to the internet. You can use the voice IP directly, use your mobile phone or your laptop, or even access to the internet. Why you need to get additional effort to do the 5G, into working? But you directly just make use of it. Will that be better?
So at least what we see, there is some advantage. Let's say when you want to deploy some larger cells. So usually if you just can connect your computer with the Starlink terminal or via, let's say, Ethernet or via Wi-Fi. However, let's say in case of emergency situation, you want to have a larger cell up to, let's say, 10 kilometers, 5G could be a solution. So in case of, let's say, disaster situation. Therefore, we think the combination of 5G radio access network and the mega constellation could be really useful for such applications.
Yes, a good point. And also you can always bring more terminal because the Starlink, the small terminal very small, but your 5G station normally quite big. Yes. Do you think that is overkilling? Do you have just for the purpose of introducing 5G? you link the 5G to the Starlink. Actually, Starlink itself implemented is supposed to be directly to provide a service to anywhere without, additional, station or base station.
Yes. Yeah, of course, this is possible, but let's say if you want directly communicate via a smartphone, then there are only two options, either Wi-Fi or the 5G private network. And let's say in some cases, it could be beneficial if you just run a private network and you really have the large coverage compared to a Wi-Fi solution.
Right. Okay. Thank you very much. We have a question from audience, and it says, can uplink limitations be overcome by using OneWeb or other satellite options? OneWeb or Starlink, uplink limitation be overcome by using.
So let's say there are some physical limitations. And at the end, it depends somehow on the size of the user terminal. And the question is whether the mega constellation will also provide let's say a larger user terminal for this enterprise application. This could be a solution. And on the other hand, they also need to allow the users to really uplink more data, because sometimes it's reduced to not overload the constellation via a single user. And therefore, they limited the overall user data rate. So at the end, there are two things which needs to be considered: the size of the user terminal, but also what the operator does.
Okay.
And yeah, currently it's kind of closed system. So basically for Starlink, you can't just use the Starlink terminal because everything is proprietary. The waveform is developed by Starlink, the terminal itself. OneWeb seems to be a little bit more open. So it seems that they have a lot of collaboration with other companies which can provide such a user terminal. And therefore, maybe it's more likely that you also can use a larger terminal.
Okay, thank you. I think quickly, another question just come up from Anna. The question is, what might be the uplink power limit, and what's the frequency band used by Starlink?
So currently, I think they mostly use the Ku band for their constellation. I don't know the exact uplink ERP, so I can't answer it right now.
What's the frequency band used?
So Starlink currently use the Ku band.
Ku band. Okay, great. I think. And hopefully that answers your question. Well, thanks, Flora. Yeah.
Just one last remark on what we observed. So basically, we use kind of a horn antenna to record the Starlink transmit spectrum, and we observed that they use kind of a multi-carrier waveform, which is very dynamic. They have multiple carriers, but they are not very static. So it seems that they switch on, switch off, switch from one satellite to another. So it seems to be a highly dynamic system. However, it's quite proprietary, and it's hard to really identify what they do. At least,
okay,
that's what we observe.
Well, thank you very much, Flora, for the talk. And we will get to the next speaker. Next speaker is from Saudi Arabia. It's King Abdullah University, Professor Ribo Wang. And Professor Wang, can you hear us and join the presentation?
Can you hear me? And this slides working well?
Yes, it's perfect. I can see and hear you.
Thank you. Good morning, good afternoon, and good evening, everyone. My name is Rebo Wang, a PhD student in Communication Theory Lab of King Abdullah University of Science and Technology. My topic is about satellite availability analysis of multi-hop routing in a multi-tier satellite constellations. This will be a technical work. This is the development progress of LEO satellites. As we can see in 5G, the satellites do not have to be supplement of the terrestrial network, and it can proceed independent routing. As has been mentioned in 6G architecture, one hot topic will be inter-satellite routing. The basic question of inter-satellite routing is how many satellites do we need in constellations, and we can proceed the independent routing. So we need to introduce the term or the KPI, which is called satellite availability. We can start with most simple scenario. As we can see, when a ground user want to communicate with another one ground user, and they are very far away, so of course they cannot communicate directly. Say the transmitter need to select a satellite as a relay. The satellite has to be visible for both users, of course. And I mean, it has been in this overlap region, which is above the horizon of both users. So the question is about the satellite availability. The question is, can we find the satellites in the overlap area, or what's the probability that we can find the satellite in the overlap area? So most of the researchers about either inter-satellite routing will mention this, and there are mainly two kinds of models in the existing literature. One is called the graph theory model. First, we need to decide a topology and select a transmitting node and receive node, and then analysis the satellite availability. But of course, we know that for low Earth orbit satellites, they are not stationary to the ground. So the topology is not always deterministic. Actually, it is dynamic. And so this kind of model may be not very suitable for LEO satellite availability analysis. And there's another kind of algorithms are random algorithms, like some machine learning algorithms, like swarm particle optimization algorithms. But they cannot provide the theoretical analysis. And if we want to analyze availability of multi-tier satellite constellation, the complexity will be extremely high. Therefore, we want to introduce a new model, which is stochastic geometry models. The spherical stochastic geometry applied in satellite constellations only in the recent 3 years to our best knowledge. There are two kinds of models in existing literature. One is called the orbit geometry model. The orbits are fixed and the positions are fixed. The inclinations of the orbits are also fixed, but the satellites are stochastic and randomly placed in on these orbits. And another model is called binomial point process, which is most commonly used in the research. But there are no orbits here. Of course, we know that if there are no orbits, the model might be not very accurate. So why we still need stochastic geometry, why we still need binomial point process? There are mainly three reasons. First, it is universal. As we can see, if we want several constellations to work together, then different constellations has different number of orbits, different inclinations. So we need many models, and if we change the constellation, then the model will have to be changed. But for binomial point process, it will be all the same. We only need the number of satellites, we only need heights, so it is more universal and flexible, and it can provide the conscience and analytical results. And if there are more than 1,000 satellites from our test, these two models will be quite similar. The results provided by these two models will be very similar. So it is accurate enough to provide a tight lower bound of satellite availability. Because of time limit, I have to omit how to derive this and directly show the results of outage probability. The outage probability is defined as we cannot find any satellite in this overlap area. So assume we already know how to get a single hop availability. I will show some numerical results. Then the results are very simple. For example, if the distance, Euclidean distance between the transmitter and receiver is very large, of course the overlap region will be smaller. If the height of the constellation is lower, then the overlap region will also be smaller, so the outage probability will be higher. And next, if there are more satellites, then the constellation, then the multi-hop routing will be more reliable, and the outage probability will be smaller. These results are quite simple, so I will extend this to the multi-hop constellation. As we can see, there are 3 tiers. One terrestrial tier. There are 300 gateways or some buoys on the sea, and combined with 2 constellations, Kepler and OneWeb, cooperate together to finish multi-tier routing. By the previous formulation, we can already get the single hop outage probabilities. They are written here. For example, if we want to start with tier 1, I mean the terrestrial tier, that's the probability we cannot find a realized satellite in tier 2 is 82%. So it means this is what the matrix means. Then, we already get this matrix, and we want to ask if we start with tier 1, what's the probability that we cannot find any realized devices in tier 1, tier 2, and tier 3? It's very simple. Just multiply them together, and we can get from tier 1, there is around 3.8%. We cannot find any realized satellites. So this is tier 2, this is tier 3. The outage probability of tier 3 is much smaller. So maybe we can think, for tier 2 strategy, it says maybe tier 3 is the best for relay routing. So we will, suppose we first look for relay satellites in tier 3, and then we choose tier 2. And then finally, if we cannot find any relay satellites, we will choose ground gateways as relay. According to this tier chosen strategy, the next question is, if we start from tier 2, then what's the probability that the next hop will be a gateway, a terrestrial tier gateway? This can be calculated by, we cannot find any satellite in tier 3, and we cannot find any relay satellites in tier 2, and we can find a gateway in tier 1. So this is the probability. Of course, we can see that from tier 2, the next hop stay in tier 1 is very low. So by repeating doing this, we can get a 3x3 matrix, and it is shown here. But we need a new matrix, which is called the transition probability matrix. There is another column and another line. This means tier 1, this means tier 2, this means tier 3. We can call this the outage tier. In Markov chain, it is called the absorption states. It means if we are already outage, we start with outage. Of course, the routing will not continue. So it will never get back to tier 1, tier 2, or tier 3. It will definitely stay in outage. And of course, if we start with tier 1, CR has about 3.8% to be enter into the outage. So this will be moved to this place. So finally, we can get a transaction probability matrix. By this matrix, then we can start to calculate the probability if we start with the threshold tier. Of course, we know most of the communication requirements are initiate with threshold tier and end at threshold tier. So we start with threshold tier. It means start with threshold tier, and we go one step. What's the probability of next step? Most likely it will stay in the third tier because threshold devices cannot directly contact with threshold devices. So the probability of staying in threshold tier will be 0. And after one hop, the outage probability will be 0.0833. Then if we assume that the transmitter and the receiver are at the opposite side of the Earth, then we can, by some stochastic geometry analysis methods, we can calculate or give the analytical results of the average number of hops. It can be calculated as this. Most simple model is we can go 1, 2, 3 until the sixth hop, and finally it means we go 6 hops, and this vector means we will take this out, take the outage probability out. But if we calculate by this results, it will be not accurate. The first reason is we know that the end is always here. The receiver, the ground user is always here. So in the last hop, it will never interrupt, or it will never outage. And the next question is, if the last relay, terrestrial or relay gateway is already in terrestrial tier, we know that terrestrial tier cannot directly communicate with terrestrial tier. So we need these 3 values to be 0. So T2 is very similar to T1, and the mean change is this column. So we go for 4 steps, and the T2 will be the last step. The final relay to the terrestrial user will definitely success. And so by this results, we can get the result obtained by analytical analysis will be very similar to the simulation, Monte Carlo simulation results. There are 2 remaining issues here. For T1, TPM1, TPM2, like this matrix, might not be always be unique. Sometimes there are many metrics calculated by the same way, but they are not unique, but the final estimated outage probability will be always unique. We can prove this. And if you still remember, how we choose the priority of the tier. We will first choose the third tier. By this vector, we choose this. But is this strategy always the best one? Actually, sometimes yes, sometimes no. We can provide 3 strategies where n is the number of tiers. One is called stationary optimal. It is the probability of staying at each tier after many hops. By this probability, we can rank the priority of the tiers. The complexity is very high, so if there are many tiers of satellites cooperate together, it will not be a very good choice. But the performance of this will be best. And when the density inspired, the complexity is very low, but the performance is not good. As we can see from this figure, the blue one will always be the upper bound, and it is getting by the method of exhaustion. And the green, the black, I mean the first two one are quite close to the ideal upper bound. And the density inspired this one, the complexity is low, but the performance is not very good, always very good. And finally, I will show some numerical results about multi-hop availability or multi-hop outage probability. We compare the performance of single tier constellation with 3-tier constellation. These are the height, and for example, there are for this position, there are 1,500 satellites in these 3 constellations, and in the 3-tier constellations, there are 500 in at the height of 600 kilometer, 500 at 900 kilometer, and the 500 satellites in 1,200 kilometer. And we can see that 3-tier one will not be much better than the 1-tier, and the performance of 3-tier is very similar to the 900 altitude one. And the next solution shows the complementarity of the ground gateways and the satellites. I mean, if we assume the outage probability is always 10%, then, for example, if we have 400 gateways, how many satellites do we need? If we add more gateways, of course, we need less satellites. This shows the result. And thank you, that's all. And I'm very willing to answer any questions.
Right. Well, thank you very much for the talk. I think we have a time for question. Is anyone have any question? I have one question for you. And in your presentation, you talk about multi-tier, multi-hops. Do you consider the intersatellite link at all within the constellation, or you simply consider without intersatellite link in your study?
Actually, we will consider, we consider some, but it will mainly consider in this one, in this outage probability. For intersatellite link, of course, they will face some free space fading, and there will be also some problems when for the beam forming, and it has already some model. And the intersatellite link, we as I can find in the research, it will be not very complex. But for the terrestrial to satellite link, it will be in stochastic geometry framework. It will be very difficult to analysis, because it will also face some like ring attenuation, like shadow radiation fading, some small scale fadings. It will be much difficult to analysis. So both of the links we will consider, and we already considered some. For example, D is the maximum distance we can reach for the satellite. Oh, sorry, theta M. Theta M is maximum range we can we can communicate. So we can change this theta M. If it's smaller, the channel model, if channel is not very good, so we can let the theta M to be smaller. Then the structure is still can still work.
Yeah, actually, if you do not consider the intersatellite link, that means you have to rely on a large number of gateway stations. If you have an intersatellite link, the number of gateway stations can be reduced. Okay. Yes. A question from audience. Did you consider LIP, low altitude platform and high altitude platform to improve availability and outrage metrics.
Yes. Yes, thank you for this very interesting question. And of course, they will improve. For example, we know that the HAP locates at the height of 20 kilometers, and the link between satellite to HAP will be free space, and the communication will be fading. The attenuation of the communication will not be very large. Then, if the HAP can be a relay, the link between HAP to terrestrial will be not very long, but also will face facing some attenuations. So if HAP can be a relay, then the availability, of course, will be much better, as well as the LAP, because the LAP will not face very will not face serious small scale fadings, because the link will be most likely to be LOS. And if we consider this, of course, not only the availability, also the data rate, the coverage probability will both be will all be improved. Thank you.
Okay, thank you, Ribawan. And can you quit the sharing? I will get my slides load up.
Okay, wait.
Can you quit your sharing? Yes. Okay, thank you.
Thank you.
Okay, can you everyone see my slides? Let me see. Let me just get okay. Can everyone hear me? Feedback?
Yes, we can hear you very well.
Oh, thank you. So this will be the last presentation. It will be me. I shared with my colleague Giovanni and from University of Siena. And after this, we will have a round table with the speakers. Hopefully the speaker will stay after my presentation. Just another reminder, tomorrow we'll start early. That's 7 o'clock in East daytime. And in US time, that's 7 o'clock. And Central European time will be in the afternoon, 1300, that's 1 o'clock in the afternoon. Okay, let me just start. So the topic I choose mainly try to report the progress we have been done with the roadmap for the satellite networking, roadmap on quality of service and quality of experience. That's myself and Giovanni. We work together and develop these slides. And also there are many colleagues, I couldn't name everybody. They actually also contributed to the work, to this part of the work. So thanks them as well. So here is the outline of my talk. So the first one, I will look into the scope of the IEEE satellite roadmap very quickly to give the context of my presentation. And then I will look into the reference architecture of the 5G and 6G satellite. Then I look into the challenge and the architecture. So then we'll come back, look into the 5G, 6G network, because all our quality of service parameter actually derived from the 5G, 6G, even 4G is a long time ago. But actually the satellite is quite different from terrestrial network. So our going back, looking into the ITU-T in a long time ago, maybe 20 or 30 years ago, they already get a group looking into the quality of service. We are going to explain what's this four viewpoint of the quality of service, how we look into the quality of service issue. Then I will look into, we call it user-centric and a network-centric view of the quality of service and network provision. So this is the way it has been the technique has been used in a long time ago, long before the integration of the satellite and the terrestrial network. Then I will look into the 5G QoS indicator. That's the 5G, and then we look into the challenges associated with the quality of service and the quality of the experience. Then I will talk about the potential solution and to address this issue. So let's look at the first one. If we look at the scope, in the scope of the satellite roadmap, looking for 5G and 6G, mainly because the 6G in the 2019, they start consider the satellite will be one of the major part of the future development. That means for the deployment of 5G, satellites considered to be one of the important part of the 5G. And also in ITU and HC and also even IETF and 5G, 6G were considered the satellite were one of the important direction to consider in the future network infrastructure. So the satellite roadmap consider the following points. One is first they look into the application and service. That means the satellite try to support the service and applications supported by the 5G and the 6G in the future. And for the reference, is considered two type of the architecture. One is we call the backhaul, another is direct access. The example of the Starlink and OneWeb, they are a kind of a backhaul. There are also the new consideration, like the Vodafone recently have a proposal looking to directly access to the satellite. That means your mobile phone do not have to do any change. You can directly connect to the satellite. Another application is the satellite IoT and edge computing. This is an important area to study. And in the physical lab, today, we have a look into the issue related to the millimeter wave for satellite network. A great challenge in that area. And then there are almost every aspect that people look into the machine learning and artificial intelligence that will be considered to be used in a different layer of the development of the evolution toward the 5G and the 6G. And I highlight the quality of service and quality of experience. That's the points I'm going to emphasize, explain more. Actually, the more important point is the security and network management. Network management will be discussed in the next 2 days. Hopefully, we'll continue to follow this workshop. And also the SDN, software-defined network, and NFV, network function, virtualization, and standardization. That's also important part of the satellite roadmap. So remember, the roadmap will be continue to evolve for the next edition. It address the details of a challenge and a potential solution for the future network. So if you look at the reference architecture, really we look into from 3 terms. One is the near terms. Near terms look into the just simple integration currently from the 5G towards the 6G, the next 10 years development. Already started looking into how we can integrate existing 5G infrastructure with the existing satellite the network without consider any of the virtualization. That's some complicated technology. Then in the midterm, we look into the 5 years term. Short term is 3 years. In 5 years term, we look into the virtualization, the concept. Basically, is follow the development of terrestrial network. We have SDN and FV. That means the development of terrestrial network virtualization and the development of virtualization and technology in the satellite are developing independently. So this is what we call a separate virtualization for the midterm. That eventually, in the long term, there are consideration the full integration of the terrestrial network and the satellite network. We call the integrated virtualization network. Sometimes we also call the federated integration. That means we provide a seamless integration between the satellite and the terrestrial network. So this is give you the context of my talk in terms of the quality of service and the quality of experience. So let's look at the challenge quality of service. So in the 5G, mainly have two important technology. One is looking to the network architecture. That's including the slicing, NFV, and also the software-defined network. So network architecture is important. And also another important aspect of development, new radio, new technology in the air interface. So these two, we call the cornerstone, personally, I would say, that supports the quality of service parameter, the challenge. So the first challenge will be end-to-end delay. And in terrestrial network, they talk about 1 millisecond, but they without consider the satellite into consideration. And they also talk about a gigabit per second of the transmission speed. So this is purely looking to the into the terrestrial network, the 5G standard, and 1 milli the connection within the one kilo square meter, and that's the terrestrial network as well. The 500 kilometer per second of the speed, and the slicing one of the technique they're going to support. So if you look at quickly compare from 4G to 5G, really it's increased the capacity in terms of throughput, try to reduce the delay, and increase the connection density, and also introduce a new network architecture. This NFV and SFV and SDN. So if you look at the parameter, they look into the future. I think this table, everybody already see this already in the keynote speak. Basically, it's the speed, the user experience speed, from the 20 gigabit per second to terabit per second, from 100 megabit per second to gigabit per second, and the spectral utilization will be much improved. The efficiency of the spectrum is improved, and maximum bandwidth, the bandwidth increased from 1 gigahertz to 100 gigahertz, and also the capacity, and also the latency has been one of the major concerns. And energy efficiency, actually, current 5G, they face a challenge. For example, because the 5G coverage area is reduced, and they need more stations. The energy efficiency increased per station, but total system increased. Latency, they try to introduce to further reduce the latency, and reliability, jitter, and mobility. All this is based on the terrestrial network. I think the latency and also some of the parameter were not to be fair to compare it to the satellite, because satellite coverage is much wider in the global scale, and terrestrial network they're more limited in the terrestrial, in mainly the city, the dense population area. So there are some in the historically, we consider the quality of service more into the ability to provide the service. If the place, the service cannot be provided, we have, satellite have we call the advantage factor. So the place you cannot provide service and a satellite can provide that quality service have to be considered separately. So if we measure the quality of service, you have two ways to look into. One is from user point of view, the customer, they see how good their quality of service is. But the service provider point of view, they look into their network, they provide a measurement, how well their service. That this service, quality of service measured from their system. But from user, they only have a perceived quality of service. For example, when you have a long distance telephone call, the quality of service. And also if you download the web page, how fast you are downloaded. That's a user aspect and a service provider aspect. And from the measurement point of view, but we can always have what we call the mean opinion score to measure the quality of the service. But this kind of a measurement is complicated. And also because the service evolve with the time, it's always complicated, difficult to carry the measurement. But from network point of view, we more use we call the network-centric view of the net quality service rather than user-centric view of the quality service. With the network-centric point of view, we can have a segment of measurement. You can measure the parameter, for example, the bit rate, the packet loss, the packet delay. You can use a machine to do the measurement. To do not rely on the user opinion. So in this way, we can, for example, satellite, we can have a network-centric measurement purely to measure the satellite segment. What's the delay? What's the packet loss? What's the throughput, for example? So this is the way typically widely used. The quality of service end-to-end measurement can be derived from this segment, measurement segment, satellite segment, or you may have many different segments, have a different, the satellite operator, they have a different measurement. Through their different measurement, we can provide end-to-end performance calculation. So actually in the IP quality service measurement, they have what we call the end-to-end performance measurement is based on the segment measurement. Because with the IP, if it's difficult to measure, the segment is not belong to you. So this we call the network-centric quality service measurement. And in terms of the 5G quality service indicator, this is a general definition. It's defined by 3GPP. But this is where we look into two aspects. One is the traffic control plan. But here, this quality service we mentioned here is more looking to the we call a user plan. A user plan function is mainly looking to the user experience. For example, when you have a video conference, when you have a download the web page, when you have a transfer, when you have a remote control interactive service. So this kind of parameter we look into is the user plan. Of course, you can look into the management plan and also we call the control plan. So that is more or less strict compared with the user, because if you have a control, have a 1 second or 2 seconds of set up link, or half second, or maybe still acceptable. But for the user interactive service, and if you delay more than 400 milliseconds, that's a user will have got a feeling they may complain about the quality service. So in terms of the characteristic, can be characterized in the following parameter. The first is that we call the resources type. You can have a guaranteed bit rate, or delay critical guarantee the bit rate, And also some of the service you do not need a guaranteed service. And also for the performance management point of view, you can have always introduce quality priority. For example, in a terrestrial network and also IP network, they also have the priority control. So some of the service you can have the high priority. Some maybe just need a low priority, depending on the quality service type. And also we have what we call the delay, packet delay budget. That means how much tolerant you can allow your packet delay. Some of the quality service, for example, the telephony service, if you say hello, if you, the reply delay for too long, that means this packet will not much useful anymore. And also if you have real-time remote control, if the delay is a delay for too long, that's not acceptable. For example, you can control the remote vehicle through the internet, or if you play a real-time game, this can be delay. Longer delay is not acceptable. Packet error, for some of the service, for example, you download your file, upload a file, the packet error is not a big, is important, critical. But if you just have, for example, timing service, every half second you provide the message. So if you lost the packet, you're just waiting for half second or even 1 second you can get the message. So you also get an average window for guaranteed bit rate and a maximum data burst. So here we can see is the challenge associated with the quality service. The first one is 20 to 23. That's very soon actually. All the satellite operator and 5G network operator and also manufacturer, they try to get a satellites and to provide a similar quality service to meet the application requirement. So this type of at the moment they consider, they call the NTN, that's a non-terrestrial network, that's including a high altitude platform and UAV and LEO, MEO, and GEO. Personally, I would say the GEO will be one of the important system to consider because GEO 95% of the user traffic at the moment is provided by the geostationary satellite service. And also the geostationary satellite actually evolved quickly. They also provide we call a high throughput satellite. They already, provide a service to many users, to the aircraft, to the mobile vehicle, to the shipping, and the military government government application. So it's important. The second one is we're looking to how the 5G system can be working together with the satellite, or how the satellite are working with the terrestrial network. For example, how the routing function can be introduced with the satellite. This we consider the routing with the terrestrial and the satellite together. So at the moment, we can have a satellite implementation independently with the terrestrial network, and also like the mobile edge computing. Well, many issues can be considered, but the 5G and the satellite function may be implemented independently. Then in the long term, and there will be the solution. We call it revolution. That means space environment will be considered with the terrestrial network together. We consider the GEO, LEO, MEO together. That means for the satellite, we expected to consider 3D satellite network. That means the GEO, MEO, and LEO. They also independent operation, of course, and also they can be interworking to provide we call a mesh system, extending to the integration with the terrestrial infrastructure. So that's the challenge for all of us working in the 5G, 6G, and the satellite community. So the potential solution is 2020, 23. That means at the moment, the satellite operator, manufacturer, they're working hard already to address the issue, particularly looking into the 5G new radio, how this can be considered with the new satellite system. So this already, the standard organization working with the satellite operator, and also the large community with the manufacturer operator, they're already working on this issue. For the second one is consider is to be the 2024 to 2025, the quality of service architecture and function for single layer network. You know, mainly for the LEO only or GEO only, together working together with the satellite community, and also consider the inter-satellite link. But the first generation of the LEO and the MEO, they do not consider the inter-satellite link, mainly because of the challenge, the difficulty they face. But in the new generation, the next phase already been considered in a satellite community. To consider the inter-satellite link is an important part of the system. Then we have a long term. Long term will be the fully integrated with multi-layer network. The quality service will be considered, integrate the routing, and all the 5G 6 routing will be considered. I think that's reached the end of my talk. I think thanks for your attention to stay so late. And I think it's time for a question. Yeah, any question, please? Any question, please?
Hi, Zil. This is Shastri. Can you hear me?
Yes, thank you.
Yes,
thank
yes,
you.
Shastri.
Yes, please.
One quick thing. I think as we go through the QS and QoE, maybe at some point of time after maybe the third phase, that we need to, don't you think we need to look into this, the HAPs and UAVs also along with it?
Of course. Okay. Sorry, but here I mainly mentioned satellite because this working group in the satellite.
Right, I know.
But UAV and HAPS, they are part of NTN. You know, satellite community. The manufacturer in the working group, I involved some of the discussion. They consider this as a part of the solution, because the challenge is more on the satellite part and the MEO in MEO LEO, but for the high HG platform or low HG platform, and also the UAV is more local. Or to the I think more related to the private network more than you know, the operational network for the operator. Yeah, thank you very much for mentioning that. They are part of the integration, considered as part of NTN.
Because what I felt was when you start putting the roadmap together and the report at some point of time, maybe the next year or so, we need to focus that part of it as not only the satellites, but to be consistent and to be comparable with the 6G activities.
Yes, of course. At the moment, many of the deployment started. For example, we got some of the demonstration experiment with wireless, with the Geo, with HTS, and also Telesat with our 5G testbed. We in the university we got 4G testbed, completed testbed with the base station, with the core network, and also for the 6G, and we are 5G testbed as well, and we are upgrading and try to evolve towards 6G. Yeah, that's will be the important part of consideration. Thank you very much for the comments. Yeah, for the suggestion. Yeah, we are working on this. Thank you.
Thank you very much. Thank you.
Thank you for your comments, Sastry, and Zili, for your nice presentation. Zili, in case if you can manage a few more one more minutes, a few more minutes, we have a few questions in the Q&A chat. At least
Okay, I can see that. Yeah.
Please, one of them at least. Yeah, thanks.
Okay, thanks. I try to address them. I think we have time before the round table. Yeah. I think the question is, sir, do you foresee economical compatibility or success for 5G, 6G over satellite? Do you believe this satellite constellation will survive the terrestrial network service? Okay, that's a very good question. Thank you very much. I can tell you, and for the geostationary satellite, they evolved toward the high throughput satellites. They will continue there. They already provide a service. I think they are a customer there. I think I have no doubt that economically will continue. They were working with 5G, 6G, but they were, for the coverage, the 5G, 6G terrestrial, they will never be able to cover the ocean, remote area economically. So I think they were, but the LEO constellation, I believe they were at least one will be survived, because the need, the application need, they can work with the 5G, 6G. But I cannot believe that all these constellation will be able to survive altogether, because I do not see the market. But I can see if the constellation, we can have working together. That don't have to be everybody to launch 10,000 or 40,000 satellites. So each of the operator have some of their constellation there. They can working together. Okay, that's the first question. Hopefully that's answer your question. The second question is that there are equivalent of a best effort quality service in satellite communication. Yes, the answer is yes. Best effort always there. That's remember, the best effort is not the best quality of service. They just try to provide the service as long as the resources are available. But I think in IP they try to reserve a certain bandwidth to be available to support the best effort of the quality of service. Thanks for the question. It's a good question. Best effort service, quality of service, or always will be there. Another question is 5G quality of service indicator packet similar to the CQI in cellular voice call. I think that's the cellular voice call will evolve. They use very little, very minimal amount of the bandwidth or resources. I think the voice call will be important, will be supported with high priority. So quality service can be supported from the packet in the future. Remember, all the future voice call will be evolved from the classical cellular voice call to the IP-based quality service call. That will be hopefully that answer your question. And also we have another colleague asked the most vendor equipment to support the quality service based on IP. priority 3 bits. I think that will be continuous there because most of the service today we use is based on IP service. Thanks for Prakash for the question. I think 5G will be more provided in the low level, for example, physical layer and MAC layer. I think that's the quality service user will see is more from an IP point of view. So thanks for the question. And also we have Pablo a question. How could be the different QE KPI, not only quality service, be taken into account from the different network function perspective? I think quality of service and QE is they are related. In the past, in the satellite network 20 years ago or 15 years ago, there are actually the mapping, direct mapping between the QS and QE. So I think in the future, we can address this issue with precisely how the mapping between quality of service and the quality of experience. They're actually mapping from ITU working group. Hopefully, that's address your question, Pablo Maduri. Okay. Okay. Well, thanks everyone, and stay to the end. I think it's time for. Could I invite all the speaker together, all the panelists to show your face? We can have a quick round table discussion. Hello, everyone. I think I quit myself. We got Florian there, Rebo, Shirley. Can we get Giovanni? Are you going to join us? Sasha, are you going to join? Okay, thank you very much, Nelson.
I'm here, but I think
you can share the round table. It's a long day.
It's a long day, and I don't know if I would suggest in any case to have something short, but I see a very qualified participant, so I will stand following you.
Okay. Okay. I think
great job.
Okay. Thanks, everyone. Stay so long. And can I have a question? Maybe I will, well, maybe just one question. And I think I asked it before, and maybe I can ask it again. I think from quality of service point of view, and a satellite may not be able to compete with terrestrial network, but satellite has its own great advantage to be able to support the coverage. And from this point of view, can everybody have a comments? Maybe I start from Nelson to give us, how we will be able to satellite community to compete or working together with our terrestrial colleague to support the future 5G, 6G network. That's a simple question. Maybe I ask the individual of our speaker and also the panelists. Can I start with Nelson, please?
Thank you very much. Yeah, that's a good question. Yes, as I mentioned, and many of you mentioned in the presentation, I think we have to focus on the strength of each system, of each component. So as it was mentioned, and you mentioned now in replying one of your questions, when you want to provide service to remote areas or to the aeronautical or maritime environment, I think these are, I would say remote, unserved and underserved regions. I think that's the strength of the satellite. And that will be really complementary to the terrestrial. And that will be mainly the focus of the satellite component of IMT 2020 or 5G or 6G. And I think in those use cases, satellite can really benefit. It can provide really good improvements and benefits for this role integrated or interworking systems to provide a continuous and globally connection with the good quality of service to the end user. Thank you.
Well, thank you very much, Nelson. And Sascha, do you want to have a comment, or you want to leave others?
I can make a comment because
yes, please. Yeah.
This is the quality of service is not only that. In general, the satellite is a big issue. It has a niche market. Say, for example, we have been thinking a long time. Every time the same question comes again and again, but it is not a competition to the terrestrial network. But at the same time, the satellites has its own niche market. For example, the people who are in the mountains or in the oceans or going on the flights and this and that. So there are those mobile services to provide. I think the terrestrial cannot handle it. So it is mainly from the point of view of the satellites, and then how to provide the good quality of service as well as quality of experience. That is what is needed, which it will be over the years. It will be done, but we have to see whether, as as you mentioned earlier, that I don't think the 40,000 and 50,000 of all these LEO satellites consisting with the 6G or 5G may not be possible. It may not from the business point of view, but some of them still survive just like anything else. And so that will happen. And I think the quality of service will be maintained at the time and the technology is there at this time. That's what my point.
Okay, thank you very much, Sascha, for your comments. Can I invite Dr. Kang to give us comments from a manufacturer point of view? Yeah, maybe standardization and manufacturer point of view.
Thank you, Professor. I want to share three aspects about the competition of satellite communication. I think at least we have three kinds of advantages. The first is we know I want to take an example in China, about China. For China, we know the terrestrial network is really very good. We can see it is very good nearly everywhere. But even this, we have at least around 20 million people can't access the terrestrial network. For these people, it's very convenient to access the satellite network. So that's the first advantages of the satellite network. The second aspect is about the case of disaster and some other abnormal case. Satellite communication is very important. And the third aspect is I think we have the hope, or we have the wish to have just one phone with the integration of satellite and terrestrial. So we can really realize we can access the communication really anytime and anywhere by just the one phone. So for the third aspect, I want to say the integration is very important. Okay, that's all.
Right. Thank you very much, Dr. Kang. Can I invite Florian to give us your view. And do you think satellite and terrestrial network, are they?
Yes, I'm happy to share my view. So I think both systems, they don't really compete. So at the end, when you have terrestrial service available, usually you always will use the terrestrial service. However, there are many use cases out there. Let's have a look at the automotive industry. So for the autonomous driving, maybe for 90% of the time, the car has terrestrial coverage. But there will be still the case where the car is not, where the car doesn't have any network connection towards a terrestrial system. And for these cases, it would be beneficial if you just have a single modem and the modem is capable to do both the terrestrial 5G protocol stack and also the NTN protocol stack. And I think, yeah, this will be the future, that you just have an integrated modem which can do both. And I think this will be important for future satellite system. They need to go away from these closed systems. So currently it seems, yeah, most of the constellation are somehow closed system. Every operator does something, yeah, for his constellation, but doesn't really have a look at the broader picture. And I think the whole industry really needs to adopt open standards and try to, yeah, use them. Otherwise, yeah, it will be quite hard to really integrate a solution for future systems.
Right. Well, thank you very much. Thank you very much. Do you have any further comments?
I just want to conclude. I mean, from one point of view, today at least a couple of people, the previous the presenters, they talked about having an integrated single system. I just want to make a comment on that. I think Electrobit in Finland a few years ago, they started developing a single terminal where you have both, you can access both the satellite as well as the terrestrial links. But I don't know why they stopped again. But I think that is the way to go. I think probably today somebody else talking about it also. And then the previous speaker, they talked about it. So there are a couple of interests. Definitely it is much more, this is the right time. Probably the technology is there or the business case is there probably. So I think that is a single terminal. Once we can develop, once we have it more and more, I think that is either you can switch to the terrestrial or the satellite. That's possible. That's all. That's all what I want to say.
Okay, thanks, Sascha. Can I invite Mr. Wang? Can you have a quick comments, or if you have any?
Yes, maybe I can talk about two applications. For example, for post-disaster, when the terrestrial network is not working well, we can, because satellites are always available, we can, at that time is in the affected areas, they can immediately use satellites to connect the internet. And another example is for low latency and ultra long distance communication. For example, if Chinese want to connect with Saudi Arabia, but the latency want to be less than maybe tenths of or even or less than 200 milliseconds, which can be achieved by LEO satellites. But for only for terrestrial network, it will be kind of challenging to reach this very low latency. So, for example, if in China, we want to control a car in Saudi Arabia, and this will be the satellite may be a very good choice. And that's all.
Okay. Well, thanks very much.
I have one comment.
Please, yeah, go ahead.
So I think at the end, our industry also needs to be honest to the user. what they can expect from future systems. So most likely you will not stream a 4K video in your car using a satellite system. However, there are still some applications, I believe, which we see in the future. Let's say low data rate communication with your phone, or also low rate communication integrated in future car system. But at the end, we also need to be honest, there are still some physical limitations which needs to be considered, and also some organizational things, or which needs to be solved on a political higher layer level. So let's say the spectrum access currently is also quite challenging. So as a constellation operator, you need to negotiate with each country to really allow broadband service. And I think these things also needs to be considered to really make the 6G vision available in the future.
Okay, I have a question from the audience. Could you please comment on the real-time application and the LEO satellites? Who will pick up this? Maybe I'll ask Florian. Can you continue? The question is, please comment on real-time application and the LEO satellites.
I think the question is, okay, what do you understand under real-time application, and which latency constraints do you have? At the end, you just have physical limits. So let's assume we have a LEO constellation in the 600 kilometer orbit. You still will have a latency of around up to 10 seconds, and you can't avoid it due to the physical limitation. So at the end, there will be many applications you can have, but if you really think you want to do some surgery via telecommunication systems, satellites might be the wrong solution. So at the end, it really depends on the use case and how latency critical the use case is, and then you need to separate them. Some of them can be solved with LEO satellites, but some of them are still very challenging, even for terrestrial systems.
Okay, well, thank you very much, everybody, for our presenter, panelists, and also our audience for your participation, to stay for so late or so early. I think it's so many interesting questions has been answered. Obviously, we cannot address all the questions at this point. We are happy to answer you in case if you send us the email or send to the coordinator for the working group. Well, thanks again. And
thanks a lot.
Probably, do you want to say anything, Giovanni, before we close down?
We are running out of time. I would like to remind tomorrow we start with a different schedule, 1 p.m. for European people and 7 for EDT time. And I would like to thank you, Zili, and the panelists and the roundtable people here, because you made a good discussion that could be for us a good input for our work on quality of service for the roadmap, because we are here also to collect good ideas for next work. Thanks a lot. Thanks a lot, everybody.
Yeah, could I also add my thanks to Matthew, working in the background, supporting the activity. And I will say goodbye to you, everyone. Hopefully see you soon in the next working group meeting. Yeah.
Thanks. Yeah, of course. Yes, please join.
Yeah, thanks. Thanks. Bye-bye.
Thank you, Matthew, for your time. See you tomorrow.
Thank you.
See you tomorrow.
Bye. Thank you.
Bye, Sastri. Hi, Sastri.
Thank you.
Good night.
Bye-bye.
Good night.
Bye-bye.
Recording stopped.